you should see here is a SageMaker user already provisioned. And you can just click here on the right, this Open Studio link. And this will take you to this Jupyter Lab-based SageMaker Studio environment. And then what you need to do, and it's all listed here in the instructions, if you scroll all the way down, the only thing you need to do, you can copy paste this git clone command. And then here in Studio, what you can do is at the bottom, click System Terminal. This will open up a terminal window. And in here, you can just issue the git clone command. So if you pasted it, you can just do it, copy paste here into this window. I've already done this, so I do have the workshop folder here. This will take a few minutes. It's a big code repo we've built. So once it's downloaded, you will see here this workshop folder popping up on the left. And today's workshop, we will walk through this first folder. So you can see here this quick start. So what you're gonna need to do is double click here in workshop and then 00 quick start. All right, and the workshop goes as follows. So we will walk you through those notebooks that you find in here one by one. So this is basically the sequence for today's session. So let me open up the first notebook, the overview. And this one here is really to help you familiarize with the environment. So if you haven't used SageMaker Studio before, or if you haven't used Jupyter Notebooks, I assume the majority of you will have. This looks familiar, but if you don't feel comfortable, this is the notebook where you can just try things out. The first important thing to note is on the top right, the kernel, which will give this notebook the compute resources and memory resources to execute, and also basic libraries. So if it shows no kernel, make sure you're selecting the Python 3 data science kernel from the dropdown. You can see that the kernel here is active when you see that there are virtual CPUs and gigabit of memory assigned. And I can see here, and you should see as well, 2 vCPUs and 4 gig of memory, which is here part on this kernel and notebook that I opened. So this means I can now execute this notebook. And again, this is really just the intro overview notebook. So a short description, I've already explained what we're going to do. So we're going to build an end-to-end SageMaker pipeline for natural language processing. We're going to use the BERT model architecture. Specifically, we're going to use a pre-trained model from the Hugging Face open source NLP library, Transformers, a very popular library. And we're going to use a product reviews dataset, the Amazon customer reviews, which contain over 150 million reviews from the Amazon.com marketplace. And we're building a text classifier trained on product review text. And the classifier is supposed to give us the rating as a prediction. So if I say, I really love this book, I really love this workshop, this should be a 5-star rating. All right, here is also a quick overview, just if you're not familiar with the AWS portfolio. Just briefly, I'll try to make it as big as I can here on my screen. AWS basically offers a variety of AI and machine learning services catered to your specific needs and use cases. So if you just want to use pre-built AI services, let's say for image recognition, for text translation, you can use the high-level AI service portfolio, which is here at the top of this deck, with a lot of the services you've probably heard about. There's Amazon Recognition for vision, there's Poly Transcribe for speech, there is Comprehend, NLP service, Translate, Textract, etc. And the great thing about those AI services is that you can literally use them with an API call. They already come with pre-trained models. So it's very easy and doesn't require too much of machine learning know-how. And you can easily embed them into your applications. And the idea is really not to reinvent the wheel if you have a service that is already satisfying your needs for your specific use case. What we're going to do today in this workshop is actually here in the middle layer of this portfolio stack. which is the family of services and capabilities around Amazon SageMaker. And over the years, Amazon SageMaker has really grown in a lot of capabilities. So really anything from labeling your data, helping you to prepare the data, create features, train models, tune models, and deploy them in production and monitor them. And also, if you're experts and you want to also build some very customized ML applications, you could always do a pick and choose from our infrastructure layer, pick the instances you like, and the frameworks we support, and just start building. But for the majority, it's really nice not to have to bother about how to manage the infrastructure and focus on the actual ML model building and training and deploying, which is exactly what SageMaker is helping you to do. All right. So again, here, hopefully everyone is familiar with that. You can execute those code cells here by clicking into those cells and just doing a Shift-Enter. Here we're rendering some HTML as well. You can see we're just being a little bit silly, showing Twitter buttons if you want to follow Chris and me. Or if you like today's workshop, you can also give us a star rating on the GitHub repo. We also like the star ratings. You can also embed iframes here in Jupyter Notebooks. So we're showing our book website here. All right, coming to the actual workshop. I've already explained what we're going to do. Here is a little bit of the details around the data set. So which columns, for example, we have, and also another nice overview. We're going to use the pre-trained model. And then we're going to create the BERT embeddings, the features for our BERT model. We're going to fine-tune it today with TensorFlow, and then train, fine-tune, and deploy the model to serve predictions. And by the end of today's workshop, you will also build your own SageMaker pipeline. And you can see a screenshot here from the DAG, the Directed Acyclic Graph, that is showing how the pipeline looks. So we're orchestrating those steps of the feature engineering, the processing, the training. We're also going to evaluate the trained model, and we'll check how the validation accuracy is performing. And if we're meeting our accuracy condition, let's say we want to have a minimum of 20% for the demo purpose, or you want to have 90% in your real production use case, you set those conditions, and then you can take an action if you're meeting the criteria. For example, register the trained model to a model registry to help you catalog different versions of the model. And we're also going to prepare for model deployment. All right, and a last note here. All of the notebooks have a last code cell, which will say release resources. And this is really housekeeping. So if you run this cell, what will happen is it will shut down the notebook kernel. And this is really just to free up the CPU and memory that we're using once we're going through all of the different notebooks here. So again, don't worry about this. This is expected. So after running this last cell, you will see that the kernel is shut down. We release the resources and can hop on to the next notebook. All right, checking in with you, Chris. Anything to share?
Yeah, it looks like so most people are in. A few folks having issues. I've sent instructions. You can just request a new account if you're still having issues. And so AWS folks that are on the line, please have people go back to that same exact event box link with in the incognito mode to get in. If you're still having issues, let us know.
All right, I'm also making sure I'm reposting the Slack link here in the GoToWebinar if somebody joined later. All right, let's move ahead. So we'll make sure to make breaks for everyone to catch up here. It's really just the initial notebooks here that I'm running. So the overview really kind of explained the use case again. If you will, please follow me along and open 01, setup dependencies. Again, make sure on the top right that you see a kernel active. So this should show Python 3 data science. And if you don't want to run cell by Shift Enter, what I do if I get lazy here, I do a restart kernel and then run all cells. This will just give a notebook a clean restart from the beginning and then execute all cells here in order. All right, and what the notebook already says with the name, set up all workshop dependencies. In this, we're really just pulling in the pip installs, pip libraries that we need to execute today. So this will run for a couple of minutes. We're checking on the Python version, which is 3.7 in this case. We're pulling in the SageMaker SDKs and keep ignoring those pip install warnings and errors. Pip is very chatty, and there's always some dependency changes happening every day. They will not affect the lab, so please just ignore them. And what we're doing here is we're pulling in the SageMaker Python SDK, which we're going to use here to interact with the SageMaker service. We're also pulling into additional libraries. One is SageMaker Debugger, which we will also see later once we fine-tune our model. Debugger lets you monitor and profile your training jobs. Really, really cool. So during the model training, you will get visibility into how the underlying resources are performing. So resource utilization, it will show you, for example, if you're running into GPU bottlenecks or CPU bottlenecks. It will give you advice and say, well, you should maybe decrease the batch sizes for training or increase the batch sizes, whatever makes sense to utilize the resources more efficiently. So really, really nice functionality. And it also captures framework metrics. So you can see how much time is spent in this case, in the TensorFlow operations, and gives you a lot of good insight. You can capture tensors if you really want to do some additional analysis. And we're going to also briefly show this in action later. And then SageMaker Experiments, which lets you catalog the different experiments you're running, the different parameters you're setting, keeping track of the different model runs. So we're also using this functionality. All right. I said we're going to mainly focus on TensorFlow today. So TensorFlow Keras as our framework of choice for this workshop. So here I'm also pip installing the TensorFlow version that we've built the code with. And I'm also pulling in the Transformers library. So this is the Hugging Face Transformers library, the open source NLP framework that is very popular, specifically for all of the pre-trained BERT models that are available. And we're going to use one of those models later on in the code, which is DistilBERT. And then we're also pulling in some additional SDKs here, PyAthena, which I will show you in the next couple of notebooks, to interact with Amazon Athena to query our data and also to register the data using the data catalog hosted by AWS Glue. All right, and you can also install like little additional tools. For some reason, here is no zip installed, so you can just do a conda install, what I'm doing here. And for example, add another tool you need, for example, zip. And I'm also making sure I have a pinned version here of matplotlib for visualizations and Seaborn. And making sure everything got installed correctly. I'm doing a little check here. So once you've run this notebook, I will actually set a local variable to true, and I will store this here. You can see the Jupyter magic command. I will store this variable here locally, and I can reuse that, for example, in the next notebook, which I will do, and make sure you installed all of the dependencies correctly. So this is also a little bit of housekeeping code. We want to make sure we can see that everybody has followed along or maybe missed one of the notebooks earlier. And the last one here, again, the last cell will release the resources, will shut down the kernel. So if you do this run all cells, at one point you will see that the kernel goes away, and this is normally the sign that you've executed the notebook, and then everything should be good. All right, we do have the dependencies set up. And this means we can actually jump in the first part here, which is getting our data ready So we have a data set, but to work with the data, we have to catalog it, register it, and then I'm going to show you how to query the data, to visualize the data, get some fun insights, and then also to run the statistical data analysis to check for any imbalances. So let's do 0-2 and start with registering the data. And because I'm always forgetting to run it, I do the bulk run, so I do a restart and run all cells. Again, this is doing a clear run here for the notebook. So what's happening in here? I'm gonna use the dataset, the Amazon Customer Reviews dataset, which is hosted in a public S3 bucket. And to work with the data, I'm gonna catalog it, register it through the data catalog service, AWS Glue. And then I'm able to use Amazon Athena to query the data sitting in S3. Amazon Athena is an interactive query service which allows you to run SQL queries on data of any size that is in your S3 bucket without the need to transform or load the data into another location. So super helpful if you're working with data sets and you just want to query, understand the data, and prepare for later for your machine learning workflow. So let me walk you through this here. So first of all, I'm importing here the needed libraries. So Boto3 should hopefully be familiar. It's the general AWS Python SDK, then the SageMaker Python SDK, which we pip installed earlier. And then I'm just setting some code here. I'm querying for the current session information, the default S3 bucket, my IAM role, which gives me the permissions to execute everything I want to do here. I'm checking the region which I'm operating in, and I'm also getting the account ID. All right, with that, let's start building the code. So here I'm importing PyAthena and the connect object, and I'm also going to use pandas in here. And as you can see here, now I'm checking this guardrail. So I'm going to retrieve this stored variable if I set up the dependencies correctly before. And this should hopefully print a true and an OK. This is really just checking that you executed the setup dependencies notebook before. In case this prints the error, then you've missed the previous notebook or it hasn't run successfully. But I guess this should be straightforward. So hopefully for everyone, this should return true and OK in the print statement. Then what we can do is we can use Amazon Athena to create a table that is pointing to the data that is sitting in the S3 bucket. To do this, we need the schema information. So we're going to register the data. That means we have to understand the columns, how the data looks like, to build this schema to register in the data catalog. And again, here's just a quick recap what our schema looks like. And we set a staging directory in S3. This is really a query cache. Think of it when you run the SQL queries on the data, the results are stored in this S3 folder as a cache location. And we also need to define the database name for the catalog, where to create this table information, the schema information. So let's just use the default that is already there in Glue, and also give this table a name. Let's call it the Amazon Reviews Parquet. So there's two different file formats that the dataset comes with. One is TSV data, tab separated, and one is Parquet data, which is a binary file format optimized for analytical queries as it's stored on a columnar basis. And we're going to use this because we're going to use this in the next notebook to run SQL queries and visualize data. Then I'm using the PyAthena connect object here, giving it the current region and this S3 staging directory, the cache directory we specified for our connection string. And with that, we can start building SQL queries. And I'm gonna show you here the printed one that's easier to read, and I'm gonna zoom in a little bit as well. So as you can see here, I'm building a SQL query, create external table, if it doesn't exist already, in the defaults database, and call it the Amazon Reviews Parquet. And note that I'm doing an external table. External means I'm pointing to an external data location, which you can see here at the bottom. is the S3 bucket that hosts our data set. So I'm not moving the data anywhere. I'm just creating the schema that is pointing to the data. And I define the schema here. So basically, I'm passing the columns and the type. So marketplace is a string value. The product ID is a string. The total votes that the product got is, or the review got, is an integer value. And we're going to be later specifically interested in the review body, which is the actual review text, and the star rating, which is the integer value of a 1 to 5 star rating, 5 being the best. Specifically to Parquet data, it also comes with the benefit that it is partitioned to optimize for queries. And in this case, it is partitioned by product category. So when we run a query saying select star from, where product category equals books, this would be a use case to optimize. And if you do a lot of those queries where you filter by categories, this is a good indicator that this should be the column you partition the data in. All right, and set a couple of more settings here. And then we can run this command. And we just need to issue one more, which is actually loading those partitions. So this is really just a convenience here, the MS-check prepare table. And with that, we can run our first SQL queries on the data. So what happened in the background here is by running this command through the Athena client, we created the entry in the data catalog in AWS Glue, defining the schema information and the location where to find the data. And now we can run SQL queries through Amazon Athena, referencing this table, which is pointing to the data in S3. So no data has been moved. We can just run the queries now because we registered the schema, which is really cool. So let's do just a simple command here to check that everything is set up correctly. So I'll do a show tables in the database. And this gives me here the table name that we just created. Looks good. So let's do an actual query. So what I can do here is I'm doing the famous select star from the default Amazon Reviews Parquet table, where product category, in this case, let's choose the digital software and limit the results to 100. And you can actually use pandas here to read the SQL and just pass in the statement and the Athena connection. And then you can pull the results straight into a pandas data frame, which I'm doing here, and then do a quick head. And you can see here, this is the data coming back. And again, it's still sitting in S3, but I can use this now to analyze, to query, to explore the data sets in preparation for my later ML workflow that I'm building. Here's another just boilerplate code to make sure that integration has worked. So we're checking that the data frame is not empty, should come back with an OK, and make sure here that you created this table and storing that information. If you want to see how the AWS Glue catalog looks like, there is a deep link. So you can click on those and they take you straight to the AWS console to the right location. So in this case, it takes you to the AWS Glue service. And some of you might know Glue from the ETL capabilities. We're using Glue as the data catalog today. And you can see here, if you click on the databases, here's the default database in the catalog, and you can list the tables. And here's the table that we just created, which the deep link already showed. And if you click in here, you can see that we registered the data. It's still pointing to the S3 bucket, and it has the schema information that we provided. And this is basically what happened here in the background of this notebook. And again, the last cell here will release the kernel resources. So quick summary, what we've done so far is we decided on our data set, which is sitting in a public S3 bucket. We used Amazon Athena to create the schema entry in the AWS Glue data catalog. And once we created this schema information, we used Athena to run SQL queries on the data sitting in the S3 bucket without moving any data. And this works super easy across any size of data. So even if you have large data sets, Amazon Athena is built on Presto. which is specifically built for running those distributed SQL queries across large data sets. So next, let's open the third notebook. And in here, we're going to visualize data. So I'm going to run some more sophisticated SQL queries than just the select star. And I'm going to ask some business-related questions to understand the data better, some questions that can help me actually later in the model building process. So this is really kind of the exploratory data analysis I'm doing here, understanding my data, preparing, and getting to know a couple of the parameters that are helpful later as well. So this is a longer notebook, so I'm going to do the same trick again. I'm doing a kernel restart and run all cells to get this notebook running. And here's an overview again of the columns that we have available. First, again, some setup code, so importing SageMaker again, Boto3, setting the variables here, session, bucket, role, region. Now I'm also going to importing NumPy, pandas, Seaborn, matplotlib, very popular visualization libraries. Quick hint also, you can set the matplotlib here configuration if you're using a MacBook to Retina displays, which will enhance the visualizations, which is also good to know. We're retrieving again, just as a check, the parameter, whether you've set up your Athena tables correctly from the previous notebook, just to make sure, otherwise this notebook will not run. So really just doing the check here that everything so far has executed correctly. So this should return the true and an OK. If not, you've missed the previous notebook or that hasn't finished correctly. So just review in case. And we're connecting to the same database and using the same table we just created. We're going to use PyAthena again and our connection. I'm setting some general Seaborn parameters here. So really just to assist with visualization. So this is like figure title sizes, face colors, line styles, etc. And I do have some helper code in here as well, which just helps me to show values on the bar plot. Let's get started with asking a couple of questions. So first of all, it's a pretty straightforward SQL query. Which product categories are the highest rated by average rating? And the way this notebook works is, first of all, we're asking a question, and then I'm showing you the SQL statement to answer that question, and then we're going to visualize it. So here you can see the SQL query should be pretty straightforward if you've been working with SQL before. Select the product category, create the average from the star rating from our table where the product category is in, and I'm just limiting it to 3 categories here, so not to run it on 150 million reviews. That's probably going to take a little bit longer for all of us to run. So let's just do it on the 3 categories here. Group it by product category and then order it by the average star rating descending. And if we run this on those 3 categories, you can see here gift card comes back with an average star rating of 4.73. So everyone is super happy about gift cards. Then the digital video games have an average of 3.85, and digital software comes back with 3.53. So let's visualize this. And here is the sample code. There's different ways probably to do this. In this case, I'm using a bar plot from the Seaborn library pre-built, and then I can just provide here labels for the axis and the actual data frame that holds the data from the previous query. And I'm setting some sizes here, making sure I'm adding a title, additional descriptions, labels, and then I can show bar plot. And here we go. So here you can see a very easy bar plot showing gift card has the highest average rating, followed by digital video games and software. And for fun, I've run those queries before on the whole data set, and I know there's always curious people in the workshops. So here is a screenshot of this query when you run it on the whole data set. And you can see that gift cards are actually indeed the highest rated given this data set, which contains reviews from 1995 to 2015. And if you scroll all the way down, digital software is indeed the least favored based on the average star rating. We do have a couple of more questions here. I'm not going to go through each. I'm just going to show you a couple more that actually also help us in the decision making on how to build the model later and what to look out for. So one thing is building the training data set. You also want to know how many data samples you have available. And especially if you're starting prototyping the model, you might start with a smaller amount of data samples just to iterate very quickly once you've built the code. And then once you're moving along and you have the code built, you then add more training data in the final stages then. So here's a query that just looks out for the number of reviews. So you can check which categories have the most number. And I'm just showing the visualization. So you can see here that gift card, video games, and software roughly have around 100 and 150,000, which is a good amount for starting to prototype. If you're looking for a larger data set, you can see here, if I query this around on the whole data set of the 150 million reviews, you can see that books actually have close to 20 million reviews. So this really helps you to kind of slice and dice if you just need a few 100,000 maybe for prototyping the first model, or if you really want to train the model on the most data available. This gives you a good indication. We're doing some fun queries here as well. So we're trying to derive some information. So for example, we do have the dates of the reviews, but we don't know when each category got introduced. So we're just making an assumption here. This might be not super correct, but we're looking for the oldest review in each category. And based on that, we're just assuming around the time when the first review came in, probably the category got introduced as well in the product catalog, right? So here's just a query that shows how to do this. So here we're looking specifically for the year of the review and checking for the oldest. So the first one here has the first review year. And then you can see here gift cards has the first review in 2004. So probably gift cards I could think of might have been introduced earlier. I'm not sure actually. Video games 2006, that might be true. Digital software 2008. And you can plot this, and here with the 3 categories, this is just not too exciting. But if you plot the date here on this time axis for all of the data points running on the whole data set, this would actually show you here that in 1999, there were 13 first reviews across unique categories. So it could be that 13 categories got introduced, right? We don't know. It might just be the way the data set got constructed, but it's a fun query to run. So what else can you do? You can do breakdowns of ratings per category. And I'm not going to bother you with the SQL or the visualization code too much. I'm going to show you the results here and explain why this is helpful. So if you look at this distribution of reviews per rating per category, you can see here the biggest chunk here in gift cards, the green bar is the 5-star ratings, and then it's stacked, followed by the 4-star, 3-star, 2-star, 1-star, etc. And what this shows you is the usual distribution of those labels. So again, we're going to use the star ratings as our label for the model to predict those ratings later. And if you think about training this model and then deploying it into production, what you want to do is you want to create a baseline and monitor the model performance against the baseline to detect if there's any drift, for example, in those data distributions. So running an analysis like this could give you a good understanding. In this case, if you're getting a review coming in the gift card category, that around 85% is usually a 5-star rating. And if you suddenly see a different distribution and suddenly 60% are 3-star ratings, there's definitely a drift from what you've established as a baseline. So this is where those distributions are really helpful. And of course, if you run this across the whole data set, it's a nice color block chart here. So I'm gonna skip a couple of the next questions because we have a lot of interesting topics here to cover today. If you want to dive deep into those notebooks, they're all available in the GitHub repo. So feel free to check them out after today's workshop in more detail and with more time as well. Basically, we're checking on how many reviews per star rating we have. And then we're doing this plot. And I will come back actually to this plot in just the next notebook when I'm discussing how you can detect statistical imbalances. And you don't have to be a pro in machine learning to spot this right away. If you see this chart, this is actually screaming for an imbalance. So we do have a lot more 5-star ratings than we would have 3, 2, or 1-star ratings. And I'm going to show you in the next notebook how we can do this a little bit more sophisticated and calculate those metrics for statistical imbalances. You could do how star ratings change over time, create averages, plot here on another timeline. And let me just jump to the last query in here, because the last one is actually really interesting for our BERT model that we're training. So if you scroll down to the question number 11, what is the distribution of review length? Or think of it as the number of words. So this is a very important parameter for the BERT model. And we're going to walk you through what's happening there and why this is in just a bit when we get to the part of the feature engineering. But in general, when you have raw text, such as our product reviews, and you want to train the NLP model, the first step you're doing is to tokenize the sentences. Let's say, I love this book, would get tokenized. And depending on the algorithm, it's usually not a single word into a token. Sometimes, they apply stemming techniques. But just to simplify the concept here, think of it as the number of words you're passing into the BERT model. In fact, it's the number of input sequence tokens. And you have to set that parameter during feature engineering and keep it during model training, etc. How do you know which parameter to choose, right? So what you can do here in this exploratory phase and what we're doing in this example as well is we're calculating the number of words per review. So you can see here in the SQL query, we're splitting the review text by space and then doing the cardinality, which will give us the number of words. And what we're doing with the number of words, we're plotting them in a distribution, in a histogram, and also calculating the percentiles, which you can do very easily here with pandas data frames. If we look at the results, we can see here the percentile distributions. So what this tells us, for example, is the shortest review has just 1 word, and the longest review has more than 5,000 words. But what we're looking here is for a good approximation, so we know what value we can choose later for the BERT model. And what helps in deciding here is if you plot this as a histogram, again, very easy, by just on the data frame that is holding the results, a plot and a hist. And this will give us a nice view here that a lot of the reviews have really 64 or less words, and there's a long tail of reviews that have more words, but are really not that many in total. And what we're deciding here, given our data, and we've tested this performs pretty well with the model, is that we're choosing here the value of 64. So this is covering 80% of our reviews in the data set as the maximum. And what will happen later, we're going to explain this again. When we feed this sequence into the BERT model, then if I do have a product review and the tokens that have more than 64, this will get truncated. And if I have shorter reviews, they will get padded up to that value. So you want to make sure you're choosing a value that captures most of the relevance in those sentences, in those reviews, but you don't need to over-provision that variable to pad up all the time because just of a few reviews that have more words. All right, so this is kind of summarizing this data exploratory stage where you're going to use, for example, Amazon Athena to run SQL queries, to slice and dice the data, to get some nice insights, and also to prepare with those helpful values here for the next steps of the model building phase. And obviously, everyone loves to visualize data. So just briefly, maybe checking in here with Chris. Anything we need to address, maybe any questions?
I think we're good. I can't say enough to the AWS folks on the line helping to answer all the questions and keep people moving forward. So thank you, team. People are starting to ask where the recording will be posted. So let me post that here. We'll post it in the next few days onto YouTube. In case you, but I think we're going to take a break soon and people will be able to get caught up. So if you're in there, also been working with Vocarium on the back end. So we think we found something. If you haven't yet gotten in and you still want to get in, there's still plenty of time. And you can definitely get caught up. Just ping me directly or one of the AWS folks and we can get you back in.
Sounds good. And let me do one more notebook and then we'll take a break here. So let's do 04. And this is always a topic. There's a lot of questions. And I want to make sure we walk through this one and then we'll take a break for everyone to maybe get some drinks or catch up here on the code. So let's open 04 and I'm also going to start running this notebook. So I'm going to do kernel restart, run all cells before I forget it. So we have the data, we explored the data, we have a good understanding. And what we just identified actually in running those exploratory questions is we saw that we have way more 5-star ratings than we do have in any of the other classes, right? So again, this should already create a flag for us that we do have imbalances. And when we train a model, we want to make sure in most cases that we're not training the model to actually recreate those imbalances, right? So in this case, we want to train the model to predict the rating based on the text and not whether this is coming from a gift card category. So the model picks up this pattern and in 80% of the cases just assigns a 5 because it just learned it and it picked up that pattern from the training data. So what you can do is use a new tool as part of the SageMaker family, SageMaker Clarify, which we introduced at last reInvent conference. And Amazon SageMaker Clarify helps you to calculate metrics, specifically pre-training bias metrics, which help you to detect those statistical imbalances in your data set. And also, once you've trained your model, you can also use Clarify to check the trained model for any bias, and also it supports explainability. And we're going to see this in action as well later on. So at this stage of our model building, we want to make sure we calculate the imbalances in the data before we start the model training. And this is what this notebook does. I know there's always a ton of questions around bias and explainability, and we have limited time in the workshop, but what I've done here is I've linked another great article from the Amazon Science team that discusses how you can use this tool, Clarify, to detect those unintended biases. So this is a good read if you want to follow up on this topic as well. So let's see how we can do this. And before I start showing you the practical application and how we can run this, I want to make sure we understand the terminology used. I've put in a link here to the documentation as well, if you want to follow up later or read in the breaks. Depending on the phase you're in, so the pre-training or the post-training of the model, you have a collection of metrics you can calculate. So the good thing is a lot of things in machine learning and deep learning go back to math, right? The same thing with those imbalances. So let's first define the term bias. Bias is really defined as an imbalance in either the training data or the prediction behavior of the model across different groups. And think of the groups such as, normally we talk about bias a lot about the sensitive groups in the data set, but it can also really be imbalances across general categories. Like in this case, the 5-star ratings are not really a sensitive column, but we can see that it's imbalanced across the different classes. And how to calculate those metrics? So again, we do have a set of metrics that can help express how imbalanced the data is. And we're going to calculate them. I'm going to show you the metrics here in a second. And Clarify will help you calculate those metrics and then combine them in a bias report pretty nicely. A label is what we know as a label. It's basically the feature that we want to predict. It's the target for the training. So in this case, in our example, the label is the star rating. What you have to define here is what is the positive label and what is the negative label, which is sometimes easier if you take another example. For example, if your model is predicting college application success given inputs, and if it's a yes, I'm admitted to college, this is the positive result. If the model says, no, unfortunately, you're not admitted, this would be a negative response. In our case, we say the 5-star rating and the 4-star ratings are positive values. And if my review gets a 1-star rating, 2 or 3, that would be the negative response. But again, this highly depends on the use case and the data you're using. But this is something you would have to define in order to calculate if any group in the data set is favored against the positive or negative outcome. And then another pretty common term in this discussion is facet. Think of facet just as a column in the dataset, a column or a feature that contains the attribute you want to check for the imbalance for the bias. And then in our case, we're going to choose the product category to see if gift cards are favored. And so the facet value would then be for product category, the values, gift cards, digital video games, digital software, etc. And also, so here we're coming to the definition of those metrics. And I've put in again the link to the documentation, which discusses those metrics in way more detail. So the good thing is, again, all of those have mathematical functions. The easiest one to understand is called the class imbalance. And if you're curious, here is the formula. So the class imbalance is basically taking the number of samples from one facet, let's see, gift card, minus the remaining number of samples. So in our case, we're doing the 3 categories, digital software and video games, subtracting and then divided by those samples summed up. And the result is a value in between the range -1 and 1. And in general, if you get a 0, this means, given this metric, the data is balanced. And if it's more towards the 1 or more towards the -1, this means there is an imbalance in either direction. And there's also a definition what this means. So in this case, a positive facing towards the +1 would indicate that the facet A, let's say gift card, has more training samples compared to the other facet values. If it's a negative towards -1, this would mean it has less. And I'm not going to explain every single metric here. It gets more complicated. But if you want to have a look here, definitely check this out. You can calculate the difference in proportions of labels, DPL. There's more famous metrics, Kolbeck-Leibler divergence, KL, Jensen-Shannon divergence. And you can see here the total list of pre-training data bias metrics, which you can calculate. It's all explained here in great detail. So jumping back to the notebook here, I'm showing you now how you can actually run those and calculate those metrics. So again, I'm setting up here just the general code, pulling in the SDKs. And what I'm doing first is I'm creating a data set which I want to check, and I'm going to pull in again the categories that we've seen before. So I'm going to use the gift card, product reviews, the digital software ones, and the digital video games, the ones we analyzed before. In this case, I'm actually pulling in the TSV files. So again, the dataset is available in Parquet and also in tab separated. For those machine learning use cases, the models and the libraries usually work on a row by row basis, where you pass in individual samples. So in this case, you would usually use CSV data, TSV data. Parquet is really suited for those analytical queries, SQL queries that we've done before. So luckily, we have the data here in TSV. I'm reading those 3 files in. And what I'm doing just here, because it's just not too many samples, I'm doing a quick concat here and concatenating those in a data frame. And I'm going to visualize again. So here I'm using all of the 3 categories together, and you can see this imbalance is actually consistent across all of the 3 categories, right? We have always more 5-star ratings. So we should definitely see some interesting metrics, right? So we're using this data set. What I'm doing is I'm uploading the data to an S3 bucket to make sure the SageMaker Clarify library has access. And now I can configure it. So let me show you how to do this. So from SageMaker, I'm importing the Clarify toolset. And I'm specifying here just a prefix for my S3 location where to store the report results, and here in the full path. And I start with the data configuration. So first I need to define what data I want to analyze. I'm pointing it here to the location where I just uploaded my CSV file. I'm passing the output location where I want to write the results to. I'm providing the label. So in this data set, star rating is my label, 1 to 5. I'm also sharing the other headers that are part of this data set. So here I can just do a column to list from the data frame and telling it this is a text CSV file format. So this is defining where is the data to analyze and what are the characteristics of the data. Then I'm defining the actual Clarify configuration for the bias metrics. And in here, I need to define the facet name I want to analyze. So again, we're choosing product category. And I need to define the positive values, the positive labels. Again, in this case, I'm using 5- and 4-star ratings as the positive outcome. In mortgage applications, loan applications, college admissions, it would probably be a yes as the positive or the no as the negative. And with that, what I can do now is I'm using a SageMaker processing job to actually run this analysis on my data. And the nice thing is, if you know SageMaker Processing Jobs, it's a construct that helps me to run code, especially in feature engineering stages, data pre-processing stages, on my data sitting somewhere in S3. And SageMaker takes care of spinning up the instances, pulling in the image to execute, pulling in your code that you provide, and then runs this. And you can run it distributed, so depending on how much data you have to process. And we already have one flavor of processing job that is coming integrated with this Clarify image that is needed to process the data. So in this case, I'm using the SageMaker Clarify processor, passing in my IAM role, and I could run this distributed. So if you have a lot of data, you could, for example, spin this up to process the data across 5 EC2 instances in parallel. You can specify the type. In our case, this is not too much data, so I can just do 1 instance and of this instance type. And then on this processing object, I can call run pre-training bias and pass in the data config, my bias configuration. I'm specifying the metrics I want to calculate. And this starts in the background here on AWS, the SageMaker Clarify processing job. We put in a couple of links here. So if you're following those links to the processing job, this will take you again to the console and straight away to this processing job. And you can see here it's I think took about 5 minutes here to complete. It has all of the information that we configured, the IAM role. You'll see the image it used. So here it's a pre-built image that already has the Clarify tool, an SDK installed in the library. This is the instance type we specified. You can see here the input data. This is exactly where we put it. And you can see everything here. You can also check the CloudWatch logs if you're curious to see what happened in the container that got executed on this instance. So you can jump to CloudWatch. And then also, if you want to peek around, have a look into the logs. Just waiting it here to load. Here's the log stream. Oh, what did I do? Click too much here. Click in here. And here are the logs. All right, this is not too exciting. We want to see the report, right? We want to see the results. So you can check the results in the S3 bucket, but for your convenience, we downloaded the results here. So you can see it creates the report in HTML, in a notebook, in a PDF, also captures the configuration. And here's a quick link that downloaded the report, and you can just open it in here. And here is the pre-training report. And as we can see here, so it analyzed the product category as the facet, the 3 values that we put in this CSV file. And we already spot that here it's imbalanced, right? Here is most reviews coming from the gift card, less in video games, and the least from digital software. And if you scroll down, you can see here the bias metrics calculated for each of those metrics that we defined. And you can see the values coming back. So class imbalance for the gift card says 0.24. So slightly imbalanced towards the positive, versus the DPL is slightly balanced towards the negative. And again, all of the definitions, how to interpret this, you can find in the documentation link that I posted here. But in general, what this is showing us, a 0 would be perfectly balanced. So we do have some work to do, right? So pretty much all values come back non-zero. So let's do this. Back in the notebook, this part is actually simple because we can still work on the data set and slice and dice it and make sure it's balanced. And what I'm doing here is really just downsampling the number of samples to be equal across each category and each class, as you can see here. By downsampling, obviously you're losing data samples. There's another technique, the upsampling, that would create more data samples to match the high watermark. In this case, for the demo, we're just taking the easy route and downsampling. So now we have approximately 1,600 data samples in each class and in each category here. So let's do the exact same thing. So I'm gonna concatenate those, upload to the S3 bucket, and I'm spinning up another Clarify job here, which is the exact same configuration, only that I'm pointing now to the newly balanced data set. I'm keeping the configuration here, positive values 5.4, facet product category, and I'm spinning up my SageMaker Clarify processing job and running the pre-training bias, calculating the exact same metrics. So everything the same, just on the other data set. And this job will also take approximately 5 minutes. So if you click on the deep link, it will take you to the second job. And if you click here on the overview, you should see the 2 jobs. Yeah, so mine took each 5 minutes. And in the meantime, this one also completed already. So we have in here a cell that checks for the completion. And I'm just going to scroll down to the report. We're all curious. So what do you think? Let's have a look. All right. I would say this looks much better, wouldn't you? So you can see here from the pie chart, now all of the 3 different categories and the values, the facet values, have an equal split of samples. And the rest of the metrics come back with a 0, which means it's balanced. And actually, the team added this visualization just recently. We got a lot of questions. Why is the class imbalance not 0? Why is this not showing a 0? Why is it coming back with a 0.33 in this case? And I think that's why the team actually added this visualization. So in the pie chart, you can see that the total is 100% of the samples. And as we do have 3 different categories here, it's an equal distribution. And hence, if you just analyze it from the viewpoint of a single facet value digital software, it's 1/3 of the samples. But if you look at the total, it's perfectly balanced.
All of what we're doing right now is basically leading up to how to create a SageMaker pipeline. And you know, someone asked on the chat something that we don't emphasize enough, I don't think, Ansha, is all of the code that we're writing is open source. We, at the end of the day, are writing TensorFlow code, we're writing either PyTorch code, Scikit-Learn, and SageMaker really is the managed cluster where we could scale outside of the notebook and onto a cluster. And so a few people have asked during the session about, you know, how do we do large data sets? Pandas can only handle so much because of the size of the notebook, you know, resources that we're using, the number of CPUs, the memory. And that's exactly what SageMaker is there for, is that we could scale out into the SageMaker cluster. So, you know, think of it like Docker images running in a managed environment. Both Ansha and I come from a like Kubernetes Kubeflow background before joining AWS. And I actually was building a company before I joined AWS called Pipeline AI, which is probably where you see some of those fake like emails that we're using as the username being generated with Pipeline AI. But my point here is, you know, we spent a lot of time building infrastructure for machine learning, and coming over to AWS, now we don't have to worry about that stuff. There's you know, teams within AWS dedicated to building out the infrastructure, managing these clusters, you know, handling scaling issues, capacity issues, right? Like anything that comes up, and that's a burden that you don't have to worry about when you're using SageMaker. So that's the real value prop of SageMaker, and that lets people like me and Ansha actually focus on data science problems, focus on, you know, natural language, and all of that sort of transitional knowledge, I'll call it, you know, which was transitioning from do-it-yourself, which is how me and Ansha kind of were, you know, started our careers, and all of that knowledge has now gone into the book to say, hey, you don't really have to do that stuff anymore. If you do want to spend nights and weekends debugging why, you know, Kubernetes doesn't work with your GPU Docker like images, you know, that's fine. But keep in mind that that's time you're not going to spend either with your family or learning about, you know, data science or learning about quantum or, you know, doing something that's really, you know, 5 years ahead, 10 years ahead, instead of debugging things that are, you know, 5 years ago, 10 years ago, right? If you're currently today dealing with, you know, GPU issues and Docker images, that's time that you're not spending focusing on, you know, real high value business tasks. So I personally do like Docker images and bash scripts and things, but at like the end of the day, I also have real business problems to solve. And so that's why I would switch to use SageMaker. And so the pipeline will actually do all of the steps pretty much that we've shown you so far. It's going to reuse the, you know, CSVs, TSVs that we have engineered. It's actually going to start from the same source TSVs that we've been showing you and perform feature engineering, and then train our BERT model. So technically fine tune the BERT model, and then ultimately we're going to evaluate the model accuracy and then deploy. So Ansha showed you how to detect bias, specifically class imbalance in our data set. That's just one type of statistical bias. There's many types, as she had discussed. So for right now, so get that 07 running. And yeah, Ansha, a bunch of bias questions here you might want to answer. Oh yes, 07 can be run without 5 and 6. Sorry, I forgot to mention that. Hopefully, let's see, someone answered there. Yes, thank you for answering that. You can run 07 on its own. 07, like I said, starts from raw data and performs all of the steps. And what like we are doing right now is just kind of filling in what the pipeline is doing. And we thought maybe we could do a version where we just jump right into pipelines. We did that once or twice. People were, kind of confused. What's going on? What's happening beneath the covers? So we've chosen this approach to sort of lead you into what you would then automate and use pipelines for long term. Okay, so I'm going to jump over back to 05. So I have already run 05. If you want, I use this quite a lot, the restart kernel and run all cells. And restart kernel, run all cells will just start top to bottom and run everything. So this is the feature engineering portion. And what's happening here is we're starting with raw text. And so, of course, machines don't really understand raw text. We need to get this into some vector space, right? And so that's where BERT comes in. So BERT has been pre-trained on millions and millions of documents, Google Books corpus, Wikipedia, and it can now represent words and phrases in vector space. And so vector space is good because now we can perform mathematical operations, we can perform linear algebra, we could do these at scale because we do have matrix like math libraries and hardware optimized for matrix math. And so this is just kind of one little sample excerpt where it would turn, for example, this review. So star rating, this is 1, 2, 3, 4, and 5. 1 is bad, 5 is good. Yes, I know that that's different throughout the world, depending on where you come from. But for this purpose, things that are great, are wonderful, are typically 4s and 5s. Things that are not good or do not use or awful are typically 1s and 2s. You'll notice on the right that the star rating gets converted into this 0 indexed label ID. So some of you might be wondering, well, why is 4 now a 3 and 2 a 1? And so all we're doing is just shifting it over. That's just how this particular implementation works. We're using a library from a company called Hugging Face. This is an open source library. It has, I have lost count, but I think 35,000 stars, maybe 50,000 GitHub stars. Very, very cool company to work with. Me and Ansha have the pleasure of actually knowing people at that company. Yes, AWS has actually partnered with this company, Hugging Face, and now has native integration with SageMaker to perform massively parallel distributed training jobs using either TensorFlow, PyTorch, and on SageMaker and using the SageMaker infrastructure. And so what we've done here is we are converting both the star rating into this 0 index vector, pretty easy because it's a number, right? It's 1 through 5, which just gets converted into 0 through 4. So that's a pretty easy transformation. And then we're actually taking the raw text, which is a product review. In this case, it's the review body column, and converting it into this BERT vector space. So like I said, BERT knows a vocabulary. And BERT has this distinct vocabulary that it has learned and has a notion of the English language. And of course, there's many different variants of BERT, as I cover here in the next slide. There's a bunch of variants, but at the end of the day, we're taking raw text. We're using a SageMaker processing job. We're using TensorFlow, Hugging Face, and Scikit-Learn. We're splitting the data for train, validation, test. I could talk about that later. We are also balancing based on what we have learned in that previous step, which is we have way more 5s than we do 3s, and so we will. In this case, we are going to downsample because we do have quite a lot of data. So in scenarios where we have lots of data, we actually can downscale or downsample and still get pretty good accuracy. And then we will ultimately create a vector for each review that we can then perform, vector math and, find similar words and has really learned language. Now, some people would say, well, it really hasn't learned language that well. There's, human intelligence that still is still needed, and that's all debatable. But yeah, so we'll show you here, in a bit, where BERT has actually learned pretty well what a positive review is versus a bad review. And today, so we're actually doing 5-class, multi-class classification. It's a form of sentiment analysis, basically, but we did want to keep it a little bit more generic, and so it's 5 classes, not just positive, negative, which is kind of boring. And so we will then be predicting whether a specific review is a 1, a 2, a 3, a 4, or a 5. And so we'll be using BERT for all this. Like I said, the first step is to transform the raw text into these BERT vectors. I had mentioned that there's multiple variants of BERT. So let me zoom out a little bit to fit this onto the screen here. Ansha calls this BERT mania. I think this slide actually made it right into our book. It's kind of a funny image. There's many different variants. There's Camembert, which is a French variant, which has learned the French language. Patentsbert, which is for U.S. patents, things like that. Bio, there's Bertcha, so just like Ansha's name, Bertcha. Just added JE, it makes it Northern German Dutch. Cybert, German BERT, which is kind of boring. You just put German and BERT, but that's learned a bit of the German language. And then clinical BERT. And there's so many variants now, it's just BERT mania. We are actually using a variant that we don't list here, but it is a smaller variant of BERT. So BERT by itself, the original, has, I think, has billions of parameters. And so very, very heavyweight. We're going to use a variant called DistillBERT that uses a statistical mechanism called distillation, which gives us a much smaller variant of BERT, about 66 million parameters, which is pretty high, but not the billions that the original BERT has, and still preserves about 97% of the accuracy. Now, DistillBERT was created by the folks over at Hugging Face, but it's totally open source, and we use it heavily. So here's a little bit more about how BERT works. I'm not going to get too much into this because it does tend to create a lot of questions and kind of distracts us a little bit. But just know that you can click into any of these links that we have here, and of course our book has many sections covering how this works. Thanks to Ansha, who was able to make sense of how BERT works. But at the end of the day, if we start from the bottom, that's the raw input coming in. BERT performs a tokenization process where it breaks up the that sentence or that specific review into tokens. And tokens are oftentimes the whole word, but BERT does figure out when parts of words can be used to construct like other words. And so this really helps with the out of vocabulary OOV problem that like a lot of early like implementations trying to learn language, where if you feed it some review that uses some weird variants like maybe text message, where you just kind of like abbreviate those kind of things, if they didn't exactly match the vocabulary that BERT that those earlier implementations that those earlier models were trained on, it just didn't know what to do. So BERT does discover sort of partial words, which are called tokens. But for the most part, like you could, typically just kind of relate or think of one token as a single word. That's not always the case, and I'll actually print out and show you some of the examples when BERT does figure that out. And so also that lets BERT, so BERT's vocabulary is 30,000 tokens, which doesn't seem like a lot, but if you have 30,000 tokens and some of those are partial words, then you can actually construct many more words from partial words, right? Okay, so the first step is to just tokenize it. This next step is to really get it into the vector form. And I think I'm going to skip through some of this, but at like the end of it, what you have are these input IDs. So if I scroll back up real quick, you'll see that we have this sort of natural language sentence and then this BERT vector. And that BERT vector is called the input IDs. And so this is the actual IDs that were learned. There's some other implementation details to BERT that are somewhat interesting, but we'll probably skip it here. You could certainly read about it up in these papers up here. But just know that the label ID is the 0 index. So if it's 4, that means it's a star rating of 5. And then there's those input IDs. You'll also see where we do have actually the original label, which is just the 1 indexed. And then we have split type. Here, this is a screenshot of just the training split. And I think we split 90% training, 5% validation, and then 5% test, which I'll speak about here in a bit. And then just keep in mind that this is the notebook version, and really was, yeah, so this was how I learned about, BERT's tokenizer, how I learned the Hugging Face API. I was just kind of playing around, right, and doing it in the notebook. When we actually run the pipeline, we'll do all of this inside of this particular script down here, this very last one, pre-process. So this is the sort of cluster production hardened version. This is more the sort of ad hoc version here in this notebook. So I say that because that's how I actually built this, and that's how most of you will start to like interact with SageMaker, is doing it here in the notebook. And then at some point you'll be moving this into the actual .py file, which will then run on the SageMaker cluster. I had mentioned this on Slack as well too, where SageMaker takes care of the like data sharding, so you can actually operate in parallel, and SageMaker will distribute those files. So let's say you have 3 like TSV files, which we do here. If we wanted to train with, perform this step of feature engineering with 3 nodes in our cluster, SageMaker will place 1 file onto each node and operate in full parallel, and then join all that data at the end. So you can also use Spark as well too. I don't think we have an example of Spark in the 0.0 quick start, but we certainly do in the book, which is the whole rest of I think it's 0.1 through 12. Okay, so yeah, back to this. So here's that Distilbert tokenizer, and this all comes from Hugging Face. And yes, once again, this is an open source library called Transformer. So I think in the setup we did a pip install transformers here somewhere. Let me find, yeah, right here, transformers. This particular workshop we're using 3.51. And that gives us the ability now to do an import from transformers. So this is the actual tokenization, and that's all that we're going to do in this specific notebook, because we're in the feature engineering phase, which we will then pull together in the pipeline here in a bit. So here's our star rating 1 through 5. We're telling it what are the relevant columns to pay attention to in our TSVs. This tokenizer is, so before I started using the transformers library, I had to write all of this tokenization code myself, and which was really annoying because I had to know how this was implemented, or go to the original paper and then write my own Python code. And I'm not really the best Python developer. And I think to be a really good Python developer for scientific Python, you like really have to know what's going on beneath the covers, down in the C libraries, down in the Fortran libraries. And so I let all of that up to these experts that are doing this on a day-to-day basis, and have thousands of other developers that are optimizing their code in like the open source world. So at like the end of the day here, we're just building some Python classes. This is just kind of code cleanliness here. We're then calling tokenize. So this is what I had to implement on my own before using the transformers. Now I could just call tokenize or tokenize. That's then going to produce a dictionary of the input IDs, and then some of the other implementation details here, which I'll skip. But just know that the input IDs is the vector in space that now represents that specific product review. We're doing one other feature transformation here, which is converting it into TF record. So TF record is a binary format that is part of the TensorFlow ecosystem, and TensorFlow loves TF record. So instead of using CSVs and TSVs or JSON, which is pretty bloated, like TensorFlow prefers this file format called TF record, and TF record is binary, so it's not really human readable. I'll actually show it to you here in a sec. There's parts of it that are readable, but the sort of intuition is when you're using a file format that's not human readable, it's typically then machine optimized. And if it is human readable, there's probably a faster way to do it, or better way to do it that's much more memory, RAM and disk like optimized. And so that's TF record. It's been here since pretty much the very beginning of TensorFlow. If you're currently doing TensorFlow today and have not used TF record, you are very likely giving up a lot of performance, and should certainly take a look at it. It's just, if you have your pipelines set up like this, where you're doing feature engineering first, you can actually then just add TF record into there, make it one extra step, and then modify your training code to then read TF record. And so some of this is it's pretty nasty code here. It's not the most intuitive. There's some weird things here, like called serialized to string, and things that I wish the TensorFlow community would have named slightly better. But at the end of the day, we have a binary file called something.tf record, and that's what we then pass into our training job, which we'll do in the 06, and then we'll pull it all together in 07. Okay, the other concept I want to express is a feature store. But actually, before I get to feature store, let me just show you what's going on here. So let's take some sample reviews. So here's a star rating of 5. Here's just some, like unique review ID. And here's a sample review, something about, Norton products, maybe Elephant Drive. This seems like this is coming from the 90s, maybe early 2000s. And we're going to tokenize these, and I want to show you what these actually look like. Okay, forget which order I do here. I think I talk about the feature store first. Okay, so I'm going to briefly explain this concept called feature store. So think of feature store as a database where you're going to store your transformed features. This is a fairly new concept. If you don't understand why you would do this, it's likely that you are just saving the these transform features in like an S3 bucket somewhere on a Google Drive somewhere, and you are potentially naming different directories and saying, these are my features that I transformed on June 28th. These are the features I transformed for this particular product category. And you likely have a whole bunch of folders, and your team has established some sort of idiom or convention that you name your directories a certain name, and that means something. So some of you might have that going on, and that works. You have to like very carefully manage these. It's difficult to sometimes lock down who can see those features. There's really no way to put in more metadata if you decide later on that you want to try some other variant of BERT. So a database of these transform features is a super powerful concept, and typically this is when your organization really starts to do high scale modeling and very, very rapid pushing out models every hour, or retraining constantly, or experimenting with all kinds of different hyperparameters, or different BERT variants, or just different natural language processing or computer vision. And you want one place to sort of track, what are you trying to do? What did that yes, like those features. So how did they actually influence your overall model accuracy? And so Feature Store has sort of come out, and it's now supported by SageMaker. There's also a bunch of startups working on something called Feature Store. And if you Google Feature Store, you'll likely see not a whole lot on this, which is why I was excited SageMaker actually pulled this in fairly early. This came out, I think, December 2020, so last year's reInvent. And really customers were starting to ask for this as part of SageMaker, because the need for this starts to become clear when you start really doing more and more modeling. Okay, so in this case, we're going to be creating these TF records and these input IDs, these BERT vectors, and we really only want to do this once, right? We have these reviews. We know that we're going to use distill BERT. We just want to generate it once and then share those features, maybe with 5 or 6 or 10 different teams, and store metadata and say whether or not that was meant for my training data set or my validation split, which variant did I use, all the things I was mentioning before. And if you don't use something like Feature Store, you will constantly be reprocessing these. And as you start to do more feature engineering and things start to get a little bit more complex, right? Like you're not just splitting the data or balancing, you're actually, creating these embeddings or these BERT vectors, right? They're sometimes called embeddings, oftentimes called embeddings. You don't want to have to regenerate these because they do take quite a bit of CPU, take quite a bit of like GPU power, memory, and you're just wasting money if you have to always regenerate these. And sometimes, people are combining features, and you hear some other team has found really good success with this particular combination of features, and you now want to reuse those features. And you could either be copying and pasting S3 buckets around, or Google Drive links around, or at worst, copying and pasting into some shared file system somewhere that is difficult to maintain. So Feature Store really pulls all of that together. So let's actually create some of these features, make these transformations here, and then store them in this Feature Store. So here's where we're actually defining our schema for a Feature Store. So like I said, it's at the end of the day, really just a database of these features that have been transformed with a lot of metadata around. I can define the data that's going in here. Here's my split type, because I'm actually going to generate a separate split for train, separate split for validation, separate split for test. I want to know all the input IDs. I want to know the raw label. I could derive it from the label ID in this case, because my label ID is actually numeric and 1 through 5. That's not always the case. The other super important field is this date. This is the date that I imported and generated those features and then pulled them into the Feature Store. So I didn't mention this because it's more of an advanced use case, but I can actually, with my Feature Store, I can say, get me all the features as of a specific point in time. And so I can actually time travel, right? So that's the cool thing here, is I can time travel back and say, I want to know what were the Netflix viewing patterns like back before COVID. As things start to recover across the world, it's not recovered across the world, I understand. But as people start to go back to work, or their viewing patterns change, maybe everyone's on vacation now because it's the summer months, these businesses might actually want to travel back in time and start to train models now as though things were back, before COVID. That's just one example, very, timely, very relevant example. There's also, quite a few other reasons and use cases. Picture like the insurance companies, for example. The insurance companies may need to time travel back and see, how did a particular person drive when they had this particular kind of car or something. I don't, yeah, that's a bad example, but there are, pretty clear use cases for time travel. And so Feature Store gives you native support to do that, to say, get me all the features as of this time for this particular, for my training split or my validation split. And so here's, just some of the API calls. I'm not going to bore you with these. Yeah, so you can go back and then reference these later. Okay, here's where we're actually calling transform. And you'll see, this is that one review up there that was talking about Norton antivirus. This is a case where BERT has taken the raw review and tokenized it. And so the word antivirus, for example, so BERT might not have learned too much about the whole word antivirus, but it has learned anti and virus, and knows the context also, knows this is in the context of software, of an application, Norton, the term no-brainer. So the word brainer was split into brain and then And so these are the 30,000, I guess, most common tokens that BERT has learned, right? And so it can then look into its little index and give us a vector. Now we've chosen 64 as our sequence length, okay? And if you remember, Ansha showed you in the visualize and said that, we were looking for a power of 2. And someone asked, why did you choose 64, or why are you even choosing power of 2? And so here's why. If I back up to Ansha's visualize section here, let me scroll all the way to the bottom. If you recall, we did this cardinality check and looked at what is the breakdown here, the distribution of number of words. Now, all that we know about here in the O3 notebook was words. We actually didn't tokenize. And that's okay. It's not exactly a one-to-one between words and tokens, but it's close. And so we actually looked, so me and Ansha, when we started, actually were using 128 for our maximum sequence length with BERT. BERT likes powers of 2, which is why we have this, 8, 16, 32, 64, 128. We could choose 256 and capture, 90%. The maximum, someone pointed out on chat, was 512 for BERT. That's BERT. That's one of BERT's biggest limitations. Now, there's something that was recently picked up by Hugging Face Transformers called Big Bird. Big Bird supports, I think, up to 4096 and does a couple tricks beneath the covers. You want to find a nice balance where you're capturing a lot of the distribution, but not necessarily all of it. And so the higher that you go, the more memory BERT will take when it's trying to train, when it's trying to learn our data set that we are going to give it in this 06 and then 07 for the pipeline. Okay, so me and Ansha actually chose 128, so that gave us 90%. We then dropped it down to 64, which covered 80%. And that actually gave us pretty good results. And so we ended up sticking with the with 64 because it was cutting our resources in half, which is good because we didn't want to pay, for a instance size that was twice as big. So if I can achieve similar performance and similar accuracy, for example, with half of the resources, half of the RAM and half of the CPU or GPU, I'm going to do that. So some of you might be thinking, well, this sounds like it's specific to the data set that I'm using. This 100% is, which is why we show you how to actually look and come up with some sort of educated guess. So if you want to try 128, that's actually what quite a lot of samples on BERT use. But if you want to get more, scientific, more methodical about this, you would actually try to, or start with your distribution. If you're dealing with larger documents, like I said, you can do, one of two things. You could either take, the first sentence of each paragraph and the last sentence of each paragraph. I've seen people do that where they have maybe 1,000, maybe 2,000 word or token documents that they're trying to train on. So I've seen people do that where they do first sentence, last sentence, which oftentimes does kind of capture the value of the paragraph. Certainly not always. Or you could also try to use something like Big Bird, which is supported by Hugging Face now and can support up to 4096. You just throw that whole document in there. Okay. At the end of the day, you'll probably want to try things that are 8,000 words and 50,000 words and try to train on whole books and stuff. And that's where you sort of have to get creative on the feature engineering side. All right, so let's assume Ansha and I just chose 64. And this is the tokens that come out. The CLS and the SCP separator, these are specific to the BERT implementation. Not going to really talk too much about that. Just know that CLS is always 101 and SEP is always 102. If you notice, this is a 0 padded array. So after tokenization, there's only 37 tokens, but we still need to put it into a 64 length array. And that's one of BERT's limitations, like I said. And so Big Bird does some tricks with this, but just know for the most common variants of BERT, they are always padding to 64. If you have something that's longer than 64, it will get truncated. And that's just one of those limitations. The input mask really is an implementation detail in more modern versions and more modern implementations of BERT. You don't really have to think about this. BERT kind of does it for us. It's just saying to pay attention. It's putting a 1 on where it should pay attention up to, and then the rest are just 0 padded. So there should be 37 of these 1s, and then the rest are 0s. Segment IDs does not apply here. In this case, we're doing a single sequence natural language processing task, which means we are passing in one single input and then trying to classify as a 1 through a 5. There are 2 sequence natural language processing tasks that BERT does support, and the most common, of course, is question answer. And so you ask a question, BERT then provides an answer, and you can train BERT on question answer pairs. If you're doing 2 sequence training, you have to say so basically this would flip between 0, 1, 0, 1, 0, 1. 0 means it's a question, 1 means it's an answer, or said more generically, 0 comes first, 1 comes next, but they're a pair. And so that's how BERT would maintain which ones are paired up. Yeah, so like I said, more like modern variants, you're not doing this low-level accounting yourself. You're just relying on Hugging Face to do that and to optimize that. So here's another example: malware. The term malware didn't quite make it to the top 30,000, but the word mal, or the token mal, does have significance, and then where does have significance. Install, so yeah, it looks like install got broken up into 3. When it's the pound, that's BERT's way of knowing that this was broken up into tokens. It's not the actual full complete word. So un is the beginning, but then all the other ones after it, install. Oh yeah, so this is actually uninstall was broken up into un and then install and a separate L. So all of that goes into BERT. Gets vector math gets processed, and that's what we'll do next in 06. And just to kind of tie everything together, here's where we can view our feature store. So here's those input IDs. I've kept the string out of it. It's not really needed for the features that we're using. So oftentimes people want to put the original data into the feature store. It's not really needed now, because you already have that data somewhere. I can join it by the review ID and basically join across tables. And here I just want the review ID. I want the date that I actually did this, which was maybe an hour ago when I ran this, and then all of the features that were engineered out of here. All right, so all that gets pulled in. I can actually query it just like a regular database. I can pull it into a data frame. This is just another view of it, the same unique ID here. And what's really cool, so Studio has a feature where you can click in here and then click Feature Store, drop down, and you can actually double click into it and look at the feature definition. And so here's time travel. I can actually change my query here. I can't actually run the query from this view, which always kind of bugged me, and I believe hopefully it is being worked on. But really, I just need this query, and then I can run it inside of my notebook, which is what I want to do anyway. Typically because I'm inside the notebook. So here's a sample query that we ran up here, and I'm saying limit 3, just bring back the top 3 and split it out. Yeah, Ansha, there's some questions in the GoToWebinar if you can.
I'll check, yep.
Yeah, a couple thank yous, and then so if you could clear those, and then okay, cool. Yeah, just saw them popping up here. All right, let's jump over to 06. So let me go back here. Let me double check that my pipeline is running. Does not look like it is. So let me rerun my pipeline. Okay. Yeah, and so if you want to just double check that 07 is running, I actually hit the run all too soon, and you should see these things going from asterisks to numbers. Mine just started running when I hit restart, so just ignore some of these warning messages here. And okay, let's back up to 06 and let me explain what's going on here. So I've just shown you how to get raw data into BERT vectors. Now we're going to fine tune a pre-trained BERT model. So I mentioned that there were pre-trained variants of BERT. We're using one called DistillBERT, which is similar to the original BERT, just much lighter weight. It's using something called distillation. So we're using a pre-trained BERT model called DistillBERT, and we are now going to introduce our domain-specific data, which is these customer reviews, and we are going to ask BERT to create a text classifier that can take a review from the wild, picture like a partner website of Amazon or off of Twitter. I could pull some phrase and say whether or not it's a 1 through a 5. I could then notify the product manager for that particular product category to say, hey, we suddenly saw a huge downturn in average review for this particular product category. What's going on? Is there something we can do on the business side? So this is a little bit lower level. So BERT was pre-trained in an unsupervised manner, and so unsupervised is where we don't really have a clear label or a clear classification. We will do that when we fine tune, which is what we're going to do in this particular notebook. But just to get us to the point where we can fine tune, BERT was pre-trained in an unsupervised manner where so basically we just put a whole bunch of data in front of BERT, and BERT learns a specific language. If we're passing it German, if we're passing it clinical healthcare data, BERT will learn the constructs and figure out the top 30,000 terms that are in there and how they're used and the context that's used, right, that those terms are used in. So this happens in like an unsupervised. So it's just, here's all of our text and then figure it out. And so the way BERT does this, there's two main things that BERT does. One is called masked language model, MLM, or sorry, masked LM typically, and then next sentence prediction, often called NSP. And so BERT is handed a document, for example, and it will mask out, I think it's 15% of the actual document, and it then tries to guess what is those 15% missing words. And it's constantly doing this. At the same time, BERT is trying to predict the next sentence from the first sentence. And so each of these, sort of by themselves are pretty primitive tasks, but combined, very, very powerful, and then sets us up for both single sequence natural language processing tasks like text classification and named entity recognition, where it can figure out that Norton is the name of this company that creates antivirus software, and also two sequence natural language processing tasks like question answer. And so, this has just proven very well. It's using the attention mechanisms between or like below the like behind the scenes. And that's where it is able to look both left to right and right to left in parallel. It can find words and sets of words and tokens and see that a particular word is being used in a specific context and therefore has a specific meaning. And so if you take the word like bank in the context of financial means something different than a riverbank. And so, so BERT can figure this out and will take all of that into account when it's then fine tuning in a supervised manner where we say this particular review is a star rating of 5. And so that's at a very high level how BERT is how we are using a pre-trained BERT model and fine-tuning it to our specific domain. Because keep in mind that BERT was not pre-trained with our customer reviews. BERT was pre-trained on more generic things like Wikipedia, which gave it a sense of the like English language. And now we are fine-tuning it. And so some of you might think this sounds like transfer learning in a traditional computer vision scenario, where we would use a pre-trained model like AlexNet, like ImageNet, something like that, that has learned what an edge is, and different colors and depth, and what a car is, or a penguin, or like an organ, and we then would transfer that learning to our new domain that's specific to us selling furniture, us selling cosmetics, right? And the two are very closely related in concept, mathematically, and sort of structurally they're different. I won't get into the details, but it's the way when you're transfer learning, you're sort of chopping off the very last layer and then just like replacing that. So if we have trained, so in the transfer learning computer vision, we will train a model to learn, let's say 1,000 different categories. So we have trains, and we have planes, we have automobiles, we have penguins. So all of those, we would just chop it off and then add in our new domain of furniture and things that are specific to our domain. In a fine-tuning sense, there's no chopping things off. We are actually adding a new classification layer, which we'll do here with Keras and TensorFlow, which then adds on our 5 classes, 1 through 5 in this case. So theoretically, or sort of conceptually, we are reusing pre-trained in both transfer learning and fine-tuning, but with the way that we actually structure our neural network is slightly different. And so here's just kind of another way to look at it: pre-trained model. We do the feature engineering, which I just showed you, and then we are adding a classification layer, which we're going to use TensorFlow, Keras. We could use PyTorch, could use MXNet. We could even use Java, by the way. I saw recently, and actually our book covers this, there's a section on it where you can use something that like AWS created, Amazon created, called Deep Java Library, I think, that can actually do BERT inside of Java, which really opens up BERT to a lot of enterprise Java use cases, which is kind of cool. And then, so the final output is a classifier. So it's going to be a TensorFlow Keras model. So Keras is really just an API now on top of TensorFlow. They used to be separate projects. Google merged them, and TensorFlow Keras are now pretty much the same thing. Keras is typically how you would be setting up these neural networks as of a couple years ago. Not many people really write low-level TensorFlow code anymore. I always kind of equate it to writing bytecode in Java. You can use higher level constructs now that handle all those like low level details. And then at the end of the day, we will have a TensorFlow model that can take just a random phrase and label it as a star rating 1 through 5. And so we can deploy this, and we can tie it to a Twitter stream, whatever we need to do. So because we're now, so like you'll see here where we're using TF record again, and we're actually decoding. So this is a function called decode. So again, this is the notebook code. When I show you the pipeline, I'll show you the actual .py file. That'll look very similar to this, but has been like more production hardened, and can handle multiple files, can do like distributed TensorFlow, all that. This is just, I'm just trying to learn the APIs. I'm just trying to give it a small amount of data and make sure that I understand how to actually write this TensorFlow code with Hugging Face. Okay, so this is where we're going to decode our TF record. And this is required when you, so I mentioned earlier, if you're doing TensorFlow and not using TF record, you can relatively easily add it to your feature engineering step. When you do that, you now have to write the sort of inverse code that's going to decode TF record and pull it into TensorFlow. And it's pretty straightforward. There's lots and lots of examples for like image classification for pretty much everything. Here's where we're going to specify hyperparameters. I had mentioned before that maximum sequence length sounds like a hyperparameter, and it certainly is. The big difference with maximum sequence length is that you have to actually use the same value during feature engineering. And so this is a hyperparameter that you need to choose before you start feature engineering. And so some of you might say, well, what if I don't know? Like, what if 64 might work, 128? You would then want to generate different, and populate your feature store with 64, with like 128, and basically run these, either overnight or for a couple days or a couple hours, and generate all of your features at 64, at 128, maybe 256, and then also run the actual training jobs that use those same hyperparameter maximum sequence length. So oftentimes hyperparameters are really only used when we're training. This is a case where we actually have to use it both feature engineering because it has to match the same sequence length that we use during training. Okay, and so conveniently, our pipeline, when we get to 07, that will only define it once and use it both in feature engineering and during training. So this was super helpful when Ansha and I, for example, were writing the book. We were going back and forth on 64, 128, and sometimes we would change it during feature engineering and then forget to do it, and then we were still using 128 during training. Now with pipelines, I define it up at the top, and it's the same value used throughout my entire pipeline, and problem solved. Some of these other ones are specific to, just fine-tuning to either BERT or to the simple classification layer, multi-class classification layer that we're going to put on top. And this is just a way to kind of configure, and this is kind of cool. This lets us use the same, so this seems kind of silly because it's like I'm mapping the 0 index to the 1 index. In some cases, I could actually change 0 to be like the string star rating, 1, star rating 2, but because this is all numeric, this seems kind of not very useful. But just know that, I'm using a pre-trained model and I can customize what the 0th index means and what these different labels mean. So not really explaining that super well, but just know that I have control. So this lets me reuse this same pre-trained model, but instead of predicting 1 through 5, I could be predicting 5 different product categories, for example. And so I would then fill this in and say the 0 index would be digital software, whatever, right? So just gives us some flexibility. It's all built into the pre-trained models that Hugging Face gives us. If you didn't use Hugging Face, like I said, then you would be writing a lot of mapping code and kind of frustrating, somewhat easy, but then also requires debugging. And then this is really where everything comes together. So this is the actual fine-tuning. So I mentioned that we're using a pre-trained model. Hugging Face has something built in here where I can say use DistillBERT. This is the TensorFlow variant. I could also use PyTorch variant, but today we're using TensorFlow. So we do TF, DistillBERT. And it's saying prepare it for sequence classification. Sequence classification, if I scroll up real quick, is text classification. There's also variants. If I was doing 2 sequence, I would say use DistillBERT for question and answer, or I'd say use DistillBERT for named entity recognition. We see a lot of NER. That's what named entity recognition is. There's a lot of NER, right, like use cases, deployments being used with BERT, which is pretty powerful. But we're using text classification, which in this API is called sequence classification. We're then defining the inputs. And so the input here are those input tokens, right? The like 101 and, we're also passing in that like input mask I briefly mentioned is the ones up until, if there were 37 tokens, there'd be 37 ones. That's pretty much handled for us, but we still have to define it as an input to this particular classifier. So at like the end of this, and yeah, Ansha and I got kind of crazy and started doing bidirectional LSTMs and other kinds of things, adding dropouts, and but at the end of this, we're applying this dense softmax layer. If you're not familiar with this stuff, yeah, don't worry about it. Like, just know that we're going to pass in the vectors, those BERT vectors. We're then going to get out a distribution between 1 and 5, right? Like across 1 and 5. And the highest value, and so this then tells us whether or not that text is a star rating 1 through 5. And so all of that comes together. This is the actual model. Oh, and here's where we define the loss function. We define the like numerical optimizer. We define the metric that we're trying to optimize. Here we are trying to find the highest accuracy. And then all of this comes together, and here's our model. So this is the actual neural network. These are the different layers, input layer, which we have control over. So keep in mind, this is 64. This means we've chosen max sequence length of 64. If you bump it up to 128 or 256, this has to get bumped up. And this is very, very easy to not get right. So keep that in mind. Here's DistillBERT. This is the pre-trained model. All of this is all the stuff that we had added afterward for our custom classifier. Here's the 66 million parameters. If we were using the original BERT, non-distill BERT, this would be in the billions. And then we run this for, I think we do it for one step or one epoch, very, very small. We are only doing this in the notebook just to make sure that we understand that we can use this API, that our data format's correct, all of the basics. We will then in pipeline tie it all together with the production version. And so some of you will ask, oh, this looks like really bad accuracy, validation accuracy 25, training accuracy 25%, validation accuracy doesn't even matter, it's so low. That's because we are just getting it to work in the notebook. There's no way that you could train at scale in a single notebook, not with this much data, not with this kind of millions or billions of parameter model. Yes, you can use GPUs, but you'll be running your notebook with a GPU, which means it's going to be running all the time, and you're really only going to use it when you click Shift-Enter here and call fit. So let's switch our thinking over. Yeah, Ansha, any questions before I get into pipelines?
We have a lot of good discussions going on here around the BERT model, what I can use it for, text classification, Q&A, entity recognition. But yeah, I think we covered most questions here. A lot of good questions around feature store, time travel functionality. Great discussions.
Cool. So ready to move forward with the pipeline stuff, right?
Yes.
Okay, give me a minute here. Grab a sip of water. Okay, and hopefully you were able to get 07 running. Mine is still running because I started it a little bit late. And then just to give everyone context, we're going to launch the pipeline. It's going to run for about 40 minutes. Maybe take a break to let it finish. And then Ansha's going to come back and we're going to analyze the results of the pipeline. We can visually view it inside of pipelines over here. So you can click this thingy over here on the left and then go to pipelines. You can actually double click it, and people always get super excited about this. I remember seeing this during reInvent and I was so excited. You can click on each of these steps and see all the hyperparameters that were used. Here's our maximum sequence length. Processing is the feature engineering step. Training is what really takes the longest. Training, I think, takes about 30 minutes. Just to manage people's expectations, the accuracy that we get from only training for 20, 30 minutes is not spectacular. However, it is better than random chance. We have 5 categories, and random chance would be 20%. I think we end up with about 30% validation accuracy, 34. In the book, me and Ancha ran for, I think, 6 or maybe 9 hours, using GPUs, and we got near, I think it was 98% accuracy. And so all the charts and everything are shown here. And yeah, so, but we are at least showing you the mechanisms to do this. If you do want to run it longer, outside of this environment, that's totally up to you. Okay, so let's go back to 07. So to give you context, we're here 07. Make sure this is running. Just do it once. Just do this restart kernel and run all once. If it's, you'll end up at a point where it just keeps saying progress, progress, and that's okay. So sorry for the scroll here. I just want to show you just so you don't. It'll do this, I think, about 30 or 40 times. It's just printing every 30 seconds, and to make sure. If you stop this or it gets stuck, we can get you back, but just let it run. Keep an eye on this circle up here in the upper right. If that thing shows busy, you're doing fine. This notebook is waiting for the cluster to finish training, and that's what I was showing here. If you go click on this thing over here in pipelines, and then click here. And then just double click. Okay, let's go back to 07. And let's show how to set this up. So I'm gonna scroll one more time, obnoxious, scroll. If you've ever set up any kind of pipeline, any kind of graph of execution, if you've ever set up like a Jenkins CI/CD, or you've used Airflow to to run a Hive query and then do something with that data, and then write it to another like database or like an S3 location or something, you will like totally understand SageMaker pipelines. What we're doing is setting up a graph of like execution. So when I say graph, I'm specifically speaking about like the ability to chain like together steps. And so as we showed in 05, there's a step where we need to do a processing job, and that's going to split our data. It's going to balance our data. First it's going to balance, then it's going to split. So balance to get us like an equal number of 1s, 2s, 3s, 4s, and 5s for the star rating. Then it's going to split and pull out 90% that we're going to use to train our model. It's going to hold out 5% for the validation to validate and take a look at the hyperparameters that we chose. Now today we are not going to do hyperparameter tuning. It just runs a little bit too long for this particular block of time. We certainly do have examples. I think I think it's chapter 8 that is focused on hyperparameter tuning, shows all how to do that. But today we will just manually choose those hyperparameters, like the maximum sequence length and some of the other ones specific to the classifier that we're using to do the fine tuning. Then we will take the raw data, we'll then convert it into TF records. Then we take those TF records and we train, which is technically fine tuning because it's a pre-trained model that we're fine tuning. The output is then a trained text classifier that we will then look at its like accuracy and make sure that that accuracy is above a certain threshold. And so I think for this workshop, we say either 20% or I might have even dropped it down to 15%. And you can change that threshold from run to run. So I can, each time I run my pipeline, I could track what was my latest accuracy. If my accuracy is 23%, the next time I run, I don't want to actually push that model into production or stage it for production unless the accuracy was higher. Okay, and so some people don't like to push anything into production like without manual reviews and all that. That's totally supported. but you can also set it up to look at like that accuracy and then push it out like automatically, or at minimum stage it, or do an A/B test, or do a canary rollout where you just send it to a small percentage of users and then compare. So there's all kinds of flexibility with SageMaker pipelines. The other cool thing about SageMaker pipelines is you can actually call basically any other service, or call your own custom code, or call into your like SAP right, like system, or basically do anything. There's this generic callback step, it's called, that can make a call and then wait for a response and then continue on conditionally based on what came back. And so Ancha and I have been working more on the like quantum side recently, right? Which we do cover in the book, I think chapter 1 or 2. And we're now actually calling into the like Amazon Bracket service, which is our quantum service, and making calls out there to do sort of hybrid classical machine learning, which we're doing today, with quantum machine learning, and then joining those results within a single pipeline. Now, we're not doing that here today, still in sort of the like early phases of getting that all wired up, but shows how you can integrate with basically any service or system. Okay. Also, there's something called conditional steps. So we can base whether or not we execute a certain path based on the result of a particular step. So yes, that's what I was saying. When we train, we'll take a look at that like accuracy, and then we will conditionally either deploy the model or not deploy it based on what was the output from the training step. So yeah, let's assume that like everything is okay. The conditional step, if we do pass that condition, we can then register the model using SageMaker Model Registry, and then from there we can set it up either for a manual type of approval or some sort of automated like approval process. So just getting that model registered, we can then do batch predictions. We can then push out as a SageMaker Endpoints, which is like a REST endpoint, and do continuous like real-time type of predictions. So yeah, and then like transform job, that's a batch transform, which was one of the options. Or yeah, we could deploy it as a REST endpoint. So when all of this is done, we'll actually see this whole thing will then execute properly. So processing, that's feature engineering. Train, we'll then do the evaluation. We'll do the conditional step. If it passes and it is above a particular threshold that we specify, we'll then register. As otherwise, we call create model. Actually both we call register and then create, which have slightly different uses. Here's kind of a horizontal way of showing the exact same thing, just gives us a little bit more real estate so we can show it in the context. So this is the exact same thing that we show up here, just flipped horizontally. So here's just a bunch of boilerplate setup code. We're going to be using, Feature Store and S3, of course, and the SageMaker service. In this case, we actually do copy the data from the public S3 bucket to the private bucket. And someone asked about this, where does this data actually get loaded? I think in the previous examples, like in the O2 notebook and O3, we were actually pointing to the public bucket. That's to show you that you can register in your Glue catalog something that's not even in your own accounts, if that data is public, of course. But here's a case where we do want to take the public data, copy it into our private accounts, and then only use that data that's in our private account. So just a slightly different way to do it, because typically we're not using public data sets only for workshop purposes or demo samples. Here we're creating the name of the pipeline. We have some boilerplate code in here because this is such a long running notebook. This will run for about 40 minutes. We see people do what we call rage clicking, which is they get frustrated and they hit, run all again and restart, and they close it down and, think something's wrong. So we have a lot of protections in place for that. This is just, battle scars of like having done this workshop so many times. But just know that we're kind of, creating the experiment. So each training run, or sorry, each pipeline run will get logged as part of an experiment. And so we can try out 64 for the max sequence length, try out 128. And we will all, and so all of those runs do get associated with one single experiment, which we can then compare side by side and then choose the best hyperparameters. So that's all that we're really doing here. I'm going to skip through some of the boilerplate, but here's where we're going to define the pipeline hyperparameters. And pipeline hyperparameters are very important because they will be used in all steps, or can be used in all steps of our pipeline, specifically this maximum sequence length. This is one that is reused across multiple steps. And so this is pretty much the exact same picture I was showing earlier. Just to put it back into context, here's the input data. These are the instance types. Someone asked earlier if we can make these like an environment variable. Here's where we're making it a pipeline variable. And we're doing everything here through code. There's also a UI that we can launch a pipeline, and it will inspect our pipeline parameters and see that we need to fill these in or stick with the defaults. Okay, so here's the maximum sequence length. This is for the feature engineering. We'll use a C52XL, just works well for us today. Balancing this data set, training split, 90%, 5-5. Here's the name of the feature store. So typically we have a single feature store or a single feature store per project. And we want to pass that in and generate these features and add them to that existing feature store. And so we can pass that in. Here's our processing job that we're going to use to transform the raw data into TF records and populate the feature store. So I mentioned that during the pipeline phase, we actually have the .py files. So let's pull up the .py file. I'm going to do a side-by-side here. Fortunately, Jupyter or SageMaker Studio lets us do this. And here's the processing step, and here's the actual .py file. And here's where I'm passing in those pipeline parameters. Okay, a bunch of boilerplate. I'm going to skip through this. Some of this should look familiar. If you recall, we're either creating or loading if we passed in a feature store, we will just load it and use it. Some of this should look familiar, where we're calling tokenize. Here, I just decided to add a little bit more documentation for the cluster version. We'll call this. This is the version that's production hardened and ready to go on the SageMaker cluster. It's got some failover code in there, and things that could happen while we're sleeping and not running it inside the notebook. We want to be able to recover from those. SageMaker helps you actually track if there are failures, and you can actually rerun the pipeline. Or you could get notified at, data scientists could get notified at 2 in the morning that their training run has failed for some reason, or maybe has plateaued, and therefore we don't need to run it for 12 hours. Whatever combination of hyperparameters that we used, for example, could have hit our target like accuracy, maybe 95% accuracy. We could stop the job and save money. So all of that can be done with SageMaker pipelines. We could set up rules, and there's tons of flexibility. And here's where we're actually parsing arguments. So this lets us, try out different hyperparameters, try out different, so this is quite a lot more flexible than the version I'd shown you in 05. So this is the notebook that ultimately led to this .py file, which is this thing down here. Here we're balancing, we're splitting. Someone asked about, are we doing the stratify? This is exactly where we're doing stratify right here. Stratifying along the star rating. So that's saying give us 90%, 5%, 5%, but do it in a way that the star ratings are all preserved. So we'll take 90% from star rating 5, 90% from 4, 3, 2, and 1, and it's stratified so that we maintain that balance that we had just created right before. So if some of this doesn't make sense to you, yeah, like don't worry about it. You will hit it at some point when you start, like using this code. You will start to see cases where you didn't stratify, and now you have all of the work that you had just done to balance the data set. You've now undone when you tried to split 90%, 5%, 5%. And we haven't really talked too much about the test split. I mentioned training split is 90%. Validation split is 5%. That's to test the hyperparameters. And then we have this third holdout called test data split. That's 5%. That really tests all of the things that we've done and gives us kind of a final test accuracy. So we'll get training accuracy, validation accuracy, and then test accuracy when we're all said and done. And that's just to make sure that data doesn't leak across those splits. You don't want to, it's called data leakage, basically. And you could artificially create a higher accurate model if you start to kind of leak what you're using in your validation data set with your test data set. And that could leak into the training data set. And then now you have a very highly accurate model that really doesn't generalize well. And so that's the purpose of, like what I consider kind of a concentric circle set of data, right? You have the training data set, and sort of broader is the validation, and then even broader is the test data set. So lots of, documentation on splits and how to do that. And now we're pulling everything into the feature. So this is populating the feature store and generating those TF record files. Okay, and next big step, we go back here to the pipeline. So that's the feature engineering. Now is the training step. And so training, this is where we're going to specify a C59XL. It's a little bit beefier, has more CPUs. We're not using GPUs today. While they are super fun, we want to, A, lower the cost for this because we do this at scale. B, when you do go to run it on your own, you can certainly bump it up to a GPU, but we do try to keep the cost of this specific portion of the workshop to be around $2 to $3. And I said that the whole book, 01 through 12, is about $25. If you do clean up all the resources properly. But this particular variant of the workshop, which we call Quick Start, that runs within 4 hours, we want to keep it, $2 to $3, so we can do this at scale and control the costs. And so here's where we're setting up the training hyperparameters. If you notice, max sequence length is not here. It's because we're going to reuse the one that was used up during feature engineering. You might notice TensorBoard. So SageMaker supports TensorBoard. SageMaker supports open source TensorFlow, supports open source PyTorch. If you are familiar with TensorBoard, it's already integrated with your like workflows, certainly something you can use, and it'll generate those TensorBoard log files, they're called, and put them in S3, and you can launch TensorBoard and point to that S3 bucket, because TensorBoard does support like S3 as a source for your files. Now we're gonna, I'm gonna show you this really slick way. This is actually one of my favorite parts, kind of geeky parts about SageMaker. Oftentimes we are, so pretty much always we are trying to optimize some metric. Here we're trying to maximize accuracy. In order to actually track the accuracy, we need a way to scrape the log lines that are being generated by either TensorFlow or PyTorch and get that data into CloudWatch. Or basically get it into anywhere. You can get it into TensorBoard, for example. Here we show, so a a very flexible mechanism that SageMaker supports is I can apply, basically any regex I want to scrape out numeric values and get them into CloudWatch. So CloudWatch would be, if you're familiar with like Prometheus or Grafana, a way to compare metrics. And also this is how I can also create rules that will stop the training job if I've plateaued, if my accuracy has not gone up within the last 5 minutes or something. I may want to stop the job because it means I've chosen a set of hyperparameters maybe that are not working well, or my accuracy plateaued or hit a peak and then started going down again. And there's no reason to keep training if I'm just going down in my accuracy. So this is really slick. And what's even cooler is you can do your own Python print that writes out a number and write a corresponding regex to pull that number out and then create your own custom metric. Now, fortunately, the PyTorch, TensorFlow support, all that support within SageMaker does all of this for you. I show it here specifically because it's one of my favorite things. Yes, having built something similar to SageMaker at my previous startup, this was something we actually hadn't gotten to yet. And so when I saw SageMaker supported this, it was super exciting. And it was as simple as just creating regex support. Because keep in mind that your Python training file or C training file or Java training file is writing out logs. It's saying this is my current accuracy. It's saying this is the current step I'm on or the current epoch. And if it's numeric and can be plotted, I want a way to be able to pull that out and to plot it and then make decisions and write rules based on that. Speaking of rules, this is one of Ancha's favorite areas, something she covered in the book. We can set up what's called SageMaker Debugger, which is a generic term, but really we use SageMaker Debugger not just for debugging, but also for profiling. And so this was one of the more exciting, at least in my opinion, releases during 2020 reInvent, where I can profile and sample every 500 milliseconds, 10 milliseconds, and generate charts that show how is my training job running. Am I set at an optimal batch size? Have I sized my cluster correctly? This is a very, very common question from pretty much all customers. How do I know which instance types to use? Is there a way to automatically tune this? Can you make suggestions? This is how you would do it. You would turn on profiling. You would make one run through. SageMaker then generates this report, which I'll show you here in a sec. That report.
And Chris, sorry to interrupt. Can you zoom in a little bit? Yeah. It's a little bit small to read.
Cool. That report will then tell you whether or not you're using the right instance size, or there's some hyperparameter that you might be able to tune better. So people use this often to tune which GPUs to use, which hyperparameters to use, batch sizes. Okay, so I also said that 06 will have a cluster version. So 06 was our training. And this is where we were testing out just to make sure that we have the inputs right and the right max sequence length sizes and the right numerical optimizer down here. And then I promised you 07 would have a cluster version. This one's actually, looks like we put it in a subdirectory source. It's called TF-BERT reviews. Let's pop this up and do it side by side. And so these are the hyperparameters that we're going to pass in. These come from the pipeline hyperparameter. So again, max sequence length is a pipeline hyperparameter. And this on the right is the production version of the 06 notebook. And so I'll go through this quickly for the sake of time, but if you remember 06, we had that TF to stillbirth for sequence classification. We had a decode method right here. decode function to convert the TF record into something that TensorFlow can use for training. This is the production cluster version that can handle checkpointing and can recover from if there's any node failures in your distributed cluster, SageMaker cluster. At scale, things fail all the time. So checkpointing, very important. That way you don't have to start the training from scratch. That's totally supported. You can use spot instances with SageMaker. So you can, I think spot instances are up to like a 90% savings. Works for, GPUs as well. Today, we're not using spot instances because sometimes these spot, if they're in high demands, you can't get them for a period of time. And so to keep this workshop on Rails and moving forward and consistent and deterministic, we use the on-demand. Our book covers each chapter pretty much. I think maybe 9 or 10 out of 12 chapters has a whole section about cost savings and improving performance. So check that out. And this is just a lot. Oh, here's where we're doing distributed training if we choose to do that. Here's some of the production hardening where we're making sure that we can actually get the pre-trained model. In case there's any failures, we do retries. And at the end of it, here's our final classification layer that, or set of layers that we're adding onto the pre-trained model. So here's our pre-trained model. Here's our layers on top, the input layers, and our dense softmax layer at the end. There's our dropout, just some of the things me and Ansha played with and worked pretty well for us. Here we could turn on checkpointing. Here's our numerical optimizer. We can turn on SageMaker Debugger, turn it off. We can turn on TensorBoard. We can turn it off. Here, just for log's sake, we can print out, just for like debugging sake, during development, this came in handy. I can print what the model looks like, just like I did in the notebook. And then, running validation, tests running. And then at like the end of all this, we're actually saving the model. And this is what Ansha is going to show you. We will deploy this model from our pipeline. Okay, and the rest is just kind of boilerplate. Here we're actually generating a confusion matrix and some other cool stuff. I'll skip through that, but just know that at the end of this, we will get a pipeline. I think I'm going to skip through the rest of this, but this is where we set up our directed acyclic graph and really wire up this. After training, we do an evaluation step. This is actually going to run. So during training, we do train and then validate. The process step, or sorry, the kind of last step is to actually run the test, the third holdout test data set on the model that was trained. That'll give us some accuracy called test accuracy. That's what we'll actually check. If it is above a certain threshold, we'll then continue to deploy. So let me skip through some of that. This will generate the evaluation report. Here, you can see that we do have one more .py file. That's for this piece I'm saying that I'm going to skip, but I'll probably end up talking about it a little bit. Here's where we're doing, we have a trained model that came out of that step of the pipeline, and now we're going to run the evaluation and then generate the test accuracy. So I'll show you all this here in a sec. Let's just get through it. If the condition passed, we'll then deploy this model, and I think that's where Ansha's going to pick up here in a sec. So this is really just, wiring up all these steps and putting the conditions. Here's that condition. Okay, so it looks like I'm doing 10% here. If the model, if like the evaluation step says that the model has a test accuracy greater than 10%, then, or sorry, greater than or like equal to, then it's going to conditionally register and then create the model and prepare it for deployment. All right, and this is where everything's going to come together. Here's where we create the pipeline with all the pipeline parameters, hyperparameters. Here we define all the steps. And we call pipeline create. That just creates the pipeline, gets it all set up. Now we actually have to call the start. And yeah, once again, this is a bunch of boilerplate here that we have introduced as battle scars during a workshop setting where people get frustrated that this is taking 40 minutes. But really all that you would need to do here is do pipeline start. Here's all the hyperparameters, max sequence length 64. We're just going to run one epic in this case. I think we do, how many steps do we do? Train batch size. Let's see, train steps, we do 50. We're not going to use TensorBoard in this case. We don't need to. And all of that should end. So this one ended okay. This one worked. Let's go and take a look at the pipeline. So once again, click over here on this left thing, go to pipelines. You'll see only one pipeline. Click on this where it succeeded. If you click on graph, that's just kind of the generic graph. If you click on succeeded, that'll take you to this. This is super exciting. This was our feature engineering step. We've been working with the studio team to get rid of that blob down there to fix it. But train, I can click on train and actually look at, okay, so this, I got validation accuracy 32%. I got training accuracy of 25%. So that's all that this train step does, is train and validate. This next step is that like evaluation process that writes out the metrics here to this S3 location, which then gets picked up by this condition step. It looks like it was true that it was greater than the 10%, and therefore registered the model and created the model. And if you have any questions about what's the difference between register and create, you could ask Ancha. She will talk about that here in a sec. Let's go back to the pipeline. I just want to point out one final thing here. Oftentimes, after, when we are training models, we want to actually look at the lineage of, showing, starting from the data that was in S3, the raw TSVs, all the way to the trained model. And so this was the other exciting feature coming out of reInvent 2020, which is lineage tracking. And so at each step, from feature engineering to training to the evaluation, so here's, processing, train, the evaluation, the condition, and then the create and the register, I can track all of the assets that were used. So I see the actual input data here was this. So this is the parent directory within S3. I see the Docker image that was used. This is just this is a SageMaker pre-built Docker image that's all open source. You can go look at it. Does the Scikit-Learn 0.23.1. Pip install also runs our .py file. So this is this .py file here, the production version of the 05 notebook. So here I can see, and then I see that the output was actually the BERT vectors in TF record format for validation, or for the train split, the validation split, and the test split. Now those outputs become the inputs for our training. And there's the training data, validation data, test data. These are the TF records. That's the Docker image that was used. And this is the actual output, which is the trained model. And I thought it actually had the train.py file here, but I don't see it. I wonder what happened to that. So this is tracking that there were inputs coming in, and then output is the actual tarred up TensorFlow trained model. Now we do the evaluation step. So there's the .py file, which is down here. It's using actually the test data set that was held out. And then there's the trained model that was generated as output from the previous step becomes the input for the evaluation. The output from the evaluation is a JSON document that then got picked up by the conditional step. This shows pending approval and some other things here that Ansha is going to talk about. So all of this comes together. Oh, and then I was talking about the profiling. Let me show you this. This is really cool. So I had mentioned that one of the big cool announcements about or from reInvent 2020 was the ability to debug and profile our training jobs. So click on this link that says Profiler Report. That's going to launch this. Make sure that you click this Trust HTML. This is one of the annoying parts about this. But so once again, click Profiler Report. Click into here. Hit the refresh if you need to. Make sure that you hit the trust. If it says distrust, that's okay. It's confusing, but if you click it, it's going to distrust it, which you don't want to do. You want to trust it. And here's the job summary. Here's how much time I spent initializing, how much time I actually spent training, how much time was used for cleanup. Here's our P99, P95s, P50s, CPU time. Let me just get to the cool. Oh, and then here's how much time was spent in training versus the evaluation. Once again, if you don't see these charts, make sure that you click Trust HTML and then maybe click the refresh. And then this is my favorite part. This is where it's saying if there's outliers, and I believe it even tells us things like we're using the wrong instance type, GPU data loader. Yeah, I think one of these says minimum. So it's just giving suggestions. And some of these don't apply because it's GPU versus CPU. Yeah, so here it says batch size. The batch size is too small. Consider running on a smaller instance type. So this is pretty cool. This earns trust with our customers, which is we're actually telling you that you're using too large of an instance for the way that your job is currently configured. You should either be using a larger batch size, or if you're fixed on that batch size for some reason, run on a smaller instance. So yes, we're actually telling you to pay us less money, use smaller resources, and you'll be better off. So really cool. So you can dive into these. And let me get back to pipeline here. And at the end of it, yeah, just showing you how to get to the actual pipeline and to poke around.
Again, on the left side menu here, you can select pipelines here, the last bottom left menu icon, and pipelines. And then you will see your BERT pipeline, which we created in the 7 notebook here. And you can double check that the execution run of this pipeline has successfully completed. Mine took approximately 40 minutes. And once it completed, make sure, as said before the break, to run 8, 9, 10, 11. They can run in parallel. And I'm going to walk you through those notebooks just now. So we've run our pipeline. We've done the pre-processing. We've done the fine-tuning. We evaluated. And as Chris pointed out, we also registered the model to the model registry. You can think about it as cataloging your models. So if you're retraining and have different versions of a model, you want to be able to have a store where you catalog the different versions. This is the model registry. We also created the model, which is preparing it for deployment here on SageMaker. So in 08, let's first start with looking at the evaluation results. So if you run 08, this will basically check that the pipeline has completed, which hopefully now for most of you should be the case. And then it lists the individual pipeline steps again. And what we want to look at is specifically the evaluation step. So this is what we're trying to parse here from all of those individual executions. So we're looking for this evaluate model step. And then we want to see where the outputs ended up. And if you remember, the evaluation step created a JSON file with the result. So here we're looking for this JSON and can basically here pull this down and then print it. And again, here you can see the output, which is basically the accuracy, which we calculated in this evaluate model.py file. And it's not too good, it's 33%, but again, we've tried to condense the training time. We waited 40 minutes now for the pipeline. You can bump up this accuracy by providing more data and training the model for longer. We didn't want you to ask to stick around for an 8-hour workshop today, so we compressed it, and this is what you get. What we can also do is the confusion metrics, which is part of this evaluation script. We're basically calculating the confusion metrics and also saving it as a PNG file. So here we're just pulling it down from the S3 bucket, which stores the evaluation results. And then we're just displaying it here. And this pretty much assembles the 33% of accuracy that we got in this just 20 minutes of training here. So this is pretty much the evaluation. We can also download the model. So here's just some sample code. We can untar it and see what we packed into this trained model. So you can see here, we do have the TensorFlow saved model version. And in the training script, we also saved it in the Hugging Face transformer specific format. We can list the artifacts again, which we've seen before, so I'm not gonna go into details here. All right, let's move on to 9 and 10. And I think most of you are excited to see how we can do the model bias analysis and how we can do the explainability. So 9 and 10 are using SageMaker Clarify again. If you remember in the beginning of today's workshop, I described how we can use SageMaker Clarify to analyze our data for statistical imbalances. And we were discussing briefly what's the difference and how we can do model bias analysis. So this is what SageMaker calls the post-training metrics. And again, here's the link to the paper if you want to follow up on this topic after today's workshop. The terminology is pretty much the same. So still we're talking with bias about an imbalance in the training data or the prediction behavior. In this case, once we have the model at hand, we can actually look now at this prediction behavior. It's going to be a different set of bias metrics though, because just given the fact that we're looking at the actual inference results. And I've put in here again the link to the documentation. It's right here in the notebook, where we can have a look at those metrics. So if we remember, before we had metrics like class imbalance, now we have metrics called, for example, the difference in positive proportions in predicted labels. So you will see a lot of those metrics have now either predicted in the name or acceptance rate, rejection rate. So we're actually observing the model prediction behavior. And again, the formulas used to calculate are all described here in this documentation, and also how to interpret the results again. So I'm not going to go into all of those details, but please feel free to read if you're interested in those. I'm going to show you how you can run it and actually test the trained model now. So we're pulling in again the boilerplate code here with the SDKs as before. And if you remember in the previous Clarify example, we started with the data. So this is what we're doing here. In this case, the test data that I'm using to run predictions against the model is in JSON lines format. And this is just to the fact that in our model, we specified that the input format is in JSON lines, and also the response from the model is in JSON lines. So this is just a little bit of preparation. We do here have a test data set available in that right format. And here you can see It's basically this kind of a JSON object per line. So it has the term features in here, and then it's the actual review text, and also has the label information in here. We're uploading this again to an S3 location, and then we can configure our Clarify job again. We're making sure the pipeline has indeed completed, otherwise we don't have the trained model at hand. So this code is really just listing the pipeline executions and checking that we do have a model available. So here you can see I'm checking for this create model step, which we did before, which is really kind of creating this model object in SageMaker. So now I can grab the pipeline model name, which I'm then going to pass in here in a second to the Clarify configuration. Again, I'm using this built-in integration in the processing jobs. So this one has already the Clarify image with all libraries, SDKs installed. I'm defining which instance count and type to run the processing job on. And more importantly now, the data config and the model config. So the data config, similar to before, is now pointing to this test data that we have at hand to run some predictions. And we also specify the label again and the JSON key that is marking the features. So in this example, the features are the review text. And again, features is literally the JSON key in there. And the headers in the sample. And in this case, dataset is application JSON lines format. Next, we need to define a model config because we need a trained model to run the predictions against. So here we pass in now this pipeline model name, which we grabbed from the pipeline, specify an instance and an instance count. So what will happen once we fire up this job is that SageMaker will spin up a shadow endpoint, deploy this trained model, run the test data against it, grab the inference results, and then calculate those post-training bias metrics. So this is why we need to specify an instance type and count here. All right, next we need to tell where in the model response is the actual prediction. And in our model signature, we have another JSON key that is called predicted label, which then holds the inference result. So this is what we're telling it here, how to parse the model output. And with that, we can configure the Clarify job again, so the bias configuration. We tell it which ones are the positive outcomes. Again, this is 5 and 4. And we want to analyze the product category as the facet. And with that, we can run the job. And in this case, you will notice before we did a run pre-training bias. Now we can just call run post-training bias, pass in the data configuration, the bias configuration, and the model config, and how to parse the prediction result. We can also specify again which methods, which bias metrics to calculate. Could be all of them, could just be a subset. And with that, it spins up again the SageMaker processing job and will bring up an endpoint, deploy the model, run predictions, capture it, and it will also shut down the endpoint again. This is why this job will approximately take, I think, around 15 minutes, because it takes time to start the instance, download the model, download the image, etc., and also clear the endpoint after it's finished. So this one is a little bit more heavy lifting. And once it's completed, you can see here the processing jobs again. So as before, Clarify runs as a SageMaker processing job in the background. And I've executed the notebook before, so this one has completed. If yours is still running, just watch my results here maybe for a little bit. And at the end, it's also generating a report again. So let me pull the report. We're going to download it here. And let's actually have a look. So this is the post-training bias metrics. To summarize, again, it spins up the endpoint, deploys the model, runs predictions. And here you can see some of the metrics it calculates. So, and this also got recently added, by the way, to show the typical metrics that we all would calculate, right? Recall, precision, accuracy, and it nicely displays it here. Not so nice with the color choice, but nicely in a visual. The false negatives, true positives, false positives for you. So you have a visual representation. And that is then used in those more complex post-training model bias metrics. And here you can see the results. So those results will rarely be in a complete, balanced, non-biased situation. What you likely do is interpret those metrics depending on your use case and make choices whether you have to look into it and try to change those metrics in a favor, or you basically define an acceptable threshold of values, and then you would observe the model when you deploy it, and as long as the model sticks within your defined thresholds, it's okay. And if you detect a drift, you would then have to trigger another action, maybe retraining the model, looking into it, investigating more. Maybe you have to set a new line, maybe you have to train a new model. But this gives you a good first indication calculating those metrics, and you can check where you would have to take action given your use case, given your data set, and the results you see in here. So this was the model bias, and I know this is a big topic, so probably there's a lot of questions still coming in. You can also, by the way, see those results in Studio in here. So we do have a little video animated GIF in here that shows how to track down those results here integrated in Studio. For now, let me move on and show you how you can do model explainability. So in the other use case for SageMaker Clarify, you can take the trained model in a similar fashion, spin up this shadow endpoint, and Clarify can apply the SHAP algorithm to explain model predictions. So what SHAP is doing, it takes the input features, runs inferences with a model, and then in each run, it will change the combination of input features to derive the importance. So which feature has the most impact on the actual inference result? And again, you will set this up pretty similar as the post-training job before. So pulling in here the libraries, preparing the test data set. The only difference here is that for explainability, you don't have to provide the actual label because you will check on a changing set of features how that impacts the prediction results. So you don't need to actually pass a label in here. You upload the data again to an S3 bucket. I'm checking that the pipeline has completed grabbing the model. So this code is exactly the same as before. And also defining my Clarify processor here with the instances to choose. I'm providing the data configuration. So again, where is my test data set and where to write the output results. Put this in here and specify again that this is a JSON lines input data set. The model configuration is also the same. So this is the model I have at hand. And I specify the instance and type to deploy. And more interesting here, and we also put in more documentation links here if you want to follow up and read about SHAP and how you can calculate those SHAP values, which Clarify is using. Basically, you can just call the Clarify SHAP configuration, and then what it needs is a baseline. And think of the baseline as just one sample line. So here we're doing just, let's say, a very simple one, okay? And in our case, we're only passing the review text. This really is powerful if you have obviously more input features. So let's say if you have 10 or 20 or even 100 input features for your models, this will nicely run and analyze which ones are really having the most relevance for the inference result. And then you can aggregate the results to have what it's called the global SHAP values. And with that, you can start the job by calling the run explainability, pass in the model config, the predicted label, which is again how to parse the result, the data config, and the SHAP config. And this spins up yet another job on SageMaker, which will take another probably 15 to 20 minutes, spinning up the endpoint, downloading the model, running the inferences, capturing the results, and also tearing down the endpoint again. So that's why it's called a shadow endpoint. I've pre-executed this notebook so we can have a look at the results. So if your job is still running, don't worry, just follow me here for a few minutes, and then you can catch up on your results as well. So here I've downloaded the report. Again, in our case, it's not too exciting because we're only passing in the review body as an actual input feature, because we made the deliberate choice that we only want to influence the predictions based on the different product text. If we had made the choice to pass in all of the dataset variables and input features and all the columns, we would see a different distribution here. We would still see that the review body hopefully has the most influence on the result, but we would probably also see that maybe the review title or also maybe the product category has an influence towards the prediction result. In our case, we simplified here, and you can see that definitely the review body influences the prediction, which is exactly what it should do. All right, so here you can see the local SHAP values are on a data sample by sample basis, and then the global ones are the aggregated. So this was quick on how you can run model explainability and see which input features contribute the most. Here is also a quick video GIF that shows the results if you're passing more input features in another use case here. So you can actually see the nice distribution and how much each input feature contributes maybe to the predictions. And with that, it's just one more notebook for us to run. And in the last one here, if you open up 11 and run that notebook as well, this will spin up a real-time inference endpoint hosted and managed by SageMaker. And let's see how we can do this. So we want to see some predictions coming back, right? Again, I'm pulling in here all of the SDKs. I'm checking that my pipeline has completed. I'm grabbing the trained model again. So we saw this code already. And what we do now is we can create a model endpoint also from the registry. So here I'm checking from the model registry, give it a name, check for the package name. So when you register the models, you mention a package name, and then you can update with the different versions, for example. And then we can call SageMaker create model, pass in the model from the registry name, give it a role with the permissions. And in this case here, I'm also specifying the container to host the model, which is also part of an entry here in the model registry. And with that, I just need here to define my actually endpoint. So I do define an endpoint configuration, which will specify again which instance type and number and also the traffic distribution for the model. So in this case, I'm sending all traffic to this single variant. If you want to do A/B testing, you could split traffic. If you want to do canary rollouts, you can split traffic. Maybe just send 5% of the traffic to one model, 95% to another, or you do a 50-50. In this case, I'm really just deploying this single model on one instance and send all the traffic to it. And we're spinning up the endpoint. It will take a few minutes, probably 5 to 7, to start again the EC2 instance, all managed by SageMaker, download the container image. So in our case, we will have a built-in TensorFlow hosting image. It will download our trained model. And then what it does, if you follow the link here to the console, it will also create a REST API, which you can embed in your applications to call the model for predictions. So my model is in service. You can check on your model following the links. Mine, I think, took around 6 minutes to spin up. And then this model endpoint is actually running here in your account. What I'm doing now is run some sample predictions. So we can either use the REST API and send predictions there, or even easier from the notebook environment, I can just use a predictor object, which is part here of the SageMaker library. And I'm passing here the endpoint name, which I want to send predictions to, the model name, which is the TensorFlow model saved model, and again, specifying its JSON lines as input and also the output from the model. And then I can just define here some sample reviews. Let's just do 2. This is great, and this is bad. And then you can send those predictions if you call the predictor predict, put in the inputs. And as you can see here, in my case, it's coming back twice with a 5. That's due to our 33% accuracy. Maybe your predictions are coming better. But this is basically how you can now send predictions and get the results back. All right, and this completes the notebook and the workshop for today. We do have one more notebook in here, which is cleaning up the resources. We keep the accounts running for, I think, 1 more hour. So you can finish your notebooks, review the code again, play around a little bit with it. And then in 1 hour, we will a GitHub star. So we're also always happy receiving GitHub stars. And with that, we're at the end of today's workshop and want to say thank you very much for joining us today. And we hope you learned a lot and enjoyed the workshop.
Yes, thank you, everyone. And thanks for all the great questions. I think, Ancha, you and I actually have to get to a meeting, so we will try to check in for questions. But yeah, we'll key it up for 1 more hour. And yeah, anything else? I think that's it.
That's it. Thanks so much, everyone. Enjoy the rest of your Monday. Bye-bye.